If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. Why does Uranus spin sideways, defying almost every expectation of how planets behave in our solar system? Uranus, the enigmatic ice giant, stands out in the solar system for a multitude of reasons, but none are more striking than its peculiar axial tilt. Unlike the other planets, which rotate more or less upright relative to the Sun, Uranus appears to roll on its side, with an axial tilt of approximately 98 degrees. This strange orientation raises profound questions about its formation, its violent past, and the forces that shaped it billions of years ago. What could have caused such an extreme deviation from the norm? Did a cataclysmic event in the distant past disrupt its natural order? Or is there something even more mysterious lurking beneath its bluish-green clouds? Beyond its curious tilt, Uranus hides a wealth of other mysteries. Its bland appearance belies the tumultuous conditions beneath its surface, with winds racing faster than any hurricane on Earth. Its magnetic field behaves chaotically, shifting and wobbling in ways that scientists are still struggling to fully comprehend. And while its icy composition sets it apart from the gas giants like Jupiter and Saturn, Uranus' atmosphere contains hints of complex chemistry that might offer clues to the origins of the solar system itself. The deeper we look, the more questions arise. Why does Uranus lack the vivid storms and dynamic cloud structure seen on Neptune, its twin in size and composition? Could there be a hidden mechanism driving its extreme weather? Or is its apparent calmness merely a facade? And what about its mysterious heat deficit? Why does Uranus radiate so little heat compared to the other giant planets? In this exploration, we'll peel back the layers of Uranus mysteries, diving into the latest research and theories that attempt to explain its unique features. From its icy core to its distant, dimly lit rings, we'll uncover the secrets of this sideways planet and consider how its story reshapes our understanding of the solar system's formation. Are you ready to journey into the unknown? The violent birth of a sideways world. To understand Uranus' peculiar tilt, we must venture back billions of years to the chaotic days of the early solar system. Astronomers believe that Uranus' dramatic orientation may have been caused by a colossal collision with an Earth-sized protoplanet, or even multiple impacts during its formation. Such a cataclysmic event would have been powerful enough to knock the planet onto its side, forever altering its rotation. But this theory raises as many questions as it answers. If Uranus was struck by a massive object, why does its orbit around the Sun remain nearly circular and stable? Wouldn't such a violent encounter leave scars visible in its atmosphere or disrupt its moons? Recent computer simulations suggest that any impact capable of tilting Uranus might have also reshaped its internal structure, trapping heat and changing how the planet evolved. However, there's an intriguing alternative theory. Some scientists propose that Uranus' tilt could result from gravitational interactions with its massive neighbors, Jupiter and Saturn. Over time, these interactions might have destabilized Uranus' axis, pushing it into its current configuration without the need for a dramatic collision. But even this explanation struggles to fully account for the planet's unique properties. The coldest planet, an unexpected paradox. Uranus holds another puzzling record. It is the coldest planet in the solar system, with temperatures plunging to a frigid minus 224 degrees Celsius, minus 371 degrees Fahrenheit. This makes Uranus even colder than Neptune, despite being closer to the Sun. Why does Uranus radiate so little heat into space compared to its fellow giant planets? Theories abound, but none are definitive. One possibility is that Uranus lost much of its primordial heat during the hypothesized collision that tilted its axis. If the impact ejected a significant portion of the planet's internal energy into space, it might explain why Uranus appears so thermally inert today. Alternatively, its unusual internal structure, dominated by a thick layer of water, ammonia, and methane ice, might act as a thermal barrier, preventing heat from escaping. Another possibility involves Uranus' lack of significant convective activity. On planets like Jupiter and Saturn, heat rises from the interior, creating dramatic weather patterns and a dynamic atmosphere. Uranus, by contrast, seems eerily calm, as if its heat is locked away beneath a stagnant outer layer. Could this be a clue to its mysterious formation, or is it simply a quirk of its icy composition? Unveiling Uranus' chaotic magnetosphere. If you were to navigate a spacecraft near Uranus, you'd quickly notice something unusual. Its magnetic field is wildly misaligned with its rotational axis, tilted by about 60 degrees. This means that Uranus' magnetic field doesn't emanate neatly from its poles like Earth's, but instead behaves unpredictably, with complex shifts and irregularities. This chaotic magnetosphere likely stems from the planet's interior, where its magnetic field is generated. Unlike Earth, where the magnetic field arises from a molten iron core, Uranus' field may originate from a thin, convective layer of salty water and ammonia surrounding its icy core. This unusual setup creates a lopsided field that wobbles and fluctuates as the planet rotates. Such a chaotic magnetic field has profound implications for Uranus' environment. Its charged particles interact with the solar wind in strange and unpredictable ways, creating auroras that are unlike anything seen elsewhere in the solar system. These auroras, however, are faint and difficult to observe from Earth, adding to the challenge of studying this enigmatic planet. A hidden system of rings and moons. At first glance, Uranus' rings seem dim and unimpressive compared to Saturn's dazzling display. But a closer look reveals a delicate and complex system that holds its own secrets. The planet's 13 known rings are composed of dark, carbon-rich material, possibly remnants of ancient moons shattered by collisions or torn apart by Uranus' gravity. Intriguingly, the rings are not uniform. Some are narrow and sharply defined, while others are more diffuse. Their composition suggests a dynamic history, with material being constantly added, removed, or redistributed by gravitational forces. Could these rings hold clues to Uranus' tumultuous past, or are they a more recent addition to its story? Uranus is also orbited by 27 known moons, each with its own unique features. Among the most fascinating are Miranda, Ariel, and Titania, whose surfaces bear evidence of violent geological activity. Miranda, in particular, is a standout with massive cliffs, deep canyons, and a surface that appears to have been reshaped multiple times. What forces could create such dramatic landscapes on a moon orbiting such a cold and distant planet? Could Uranus harbor the building blocks of life? While Uranus may seem inhospitable, some scientists speculate that its interior could offer conditions suitable for prebiotic chemistry, the chemical processes that precede the emergence of life. Deep within its icy mantle, pressures and temperatures may create an environment where water and ammonia form a superionic state, allowing for the movement of ions and the possibility of complex chemical reactions. Even more tantalizing is the idea that some of Uranus' moons could host subsurface oceans, similar to the icy moons of Jupiter and Saturn. These hidden oceans might contain the ingredients necessary for life, shielded from the harsh conditions of space by thick ice crusts. Could the same forces that shaped Uranus also provide a sanctuary for life beneath its moon's frozen surfaces? The mysteries of Uranus are as vast as the planet itself. With every discovery, new questions arise, pushing the boundaries of our understanding and reminding us how much we still have to learn. Shall we delve even deeper into these enigmas? The winds of Uranus, a hidden fury beneath a calm surface. At first glance, Uranus appears deceptively tranquil. Its bluish-green hue, a result of methane absorbing red light in the atmosphere, gives the impression of a serene and unchanging world. However, beneath this calm exterior lies an atmosphere of extraordinary activity. Winds on Uranus can reach staggering speeds of up to 900 kilometers per hour, 560 miles per hour, rivaling the most extreme weather systems on Earth. These winds are confined to a relatively thin layer of the atmosphere, with deeper layers showing little to no movement. What drives these fierce winds in a planet so distant from the sun, receiving only a fraction of the sunlight that fuels weather systems on Earth? Scientists believe that the planet's internal dynamics, rather than solar energy, are the primary culprits. Subtle imbalances in Uranus' atmospheric chemistry and the planet's unusual heat distribution may create powerful jet streams that circle the planet. Even more intriguing is how these winds interact with Uranus' extreme seasons. With a tilt of nearly 98 degrees, Uranus experiences the most dramatic seasonal variations in the solar system. Each pole is bathed in 42 years of continuous sunlight followed by 42 years of darkness. These prolonged periods of light and shadow might intensify atmospheric circulation, creating long-lasting weather patterns that remain poorly understood. The chemistry of a bluish-green world. The mesmerizing hue of Uranus is only the beginning of its atmospheric mysteries. While methane is the primary factor behind its color, deeper layers contain traces of hydrogen sulfide, ammonia, and other complex molecules that hint at fascinating chemical processes. Unlike Jupiter and Saturn, Uranus lacks the prominent belts and zones caused by the upwelling of gases, making its atmosphere appear unusually uniform. But appearances can be deceiving. Beneath this uniformity, Uranus may harbor storms and vortices that are hidden from view. Recent observations using advanced telescopes have revealed subtle variations in the atmosphere, including bright spots that may represent massive storm systems. These findings suggest that Uranus' atmosphere is far more dynamic than previously believed, with processes that are just beginning to be uncovered. Understanding Uranus' atmospheric composition also provides clues about its origin. The planet's abundance of volatile compounds like methane and hydrogen sulfide suggests that it formed in the colder, outer regions of the solar nebula. Could these icy components reveal the conditions of the early solar system, frozen in time within Uranus' atmosphere? The role of ice in Uranus' identity. Uranus is classified as an ice giant, a distinction that sets it apart from the gas giants Jupiter and Saturn. This classification stems from its unique internal composition, dominated by ices such as water, ammonia, and methane. These substances are not icy in the traditional sense. Under the immense pressures and temperatures within Uranus, they exist as dense, exotic fluids. The planet's interior is thought to consist of a rocky core surrounded by a thick mantle of icy material, with the outermost layer composed of hydrogen and helium gas. This layered structure makes Uranus a fascinating case study for understanding planetary evolution. How did it accumulate such an unusual mixture of materials? And why does it differ so dramatically from the gas giants? One hypothesis is that the region where Uranus formed was rich in water and other volatile compounds, allowing it to gather these ices during its early stages. Alternatively, its icy composition could result from a later migration, where the planet formed closer to the Sun before moving outward. This idea aligns with theories of planetary migration, which suggest that the early solar system was a chaotic and dynamic place. Uranus' mysterious moons, geological wonders in the darkness. The moons of Uranus are as enigmatic as the planet itself. Orbiting in near-perfect alignment with Uranus' equator, they share the planet's extreme tilt, resulting in bizarre seasonal effects. Among these moons, Miranda stands out as one of the most unusual objects in the solar system. Miranda's surface is a patchwork of jagged cliffs, smooth plains, and massive chasms, some of which are 12 times deeper than the Grand Canyon. These features suggest that the moon has undergone repeated cycles of tectonic activity, despite its small size and apparent lack of internal heat. Could Miranda's dramatic geology be the result of tidal forces exerted by Uranus? Or is there another, yet unknown, process at work? Ariel and Titania, two of Uranus' larger moons, also display evidence of past geological activity. Bright streaks across their surfaces hint at cryovolcanism, where icy materials, rather than molten rock, erupt from the interior. If these moons once harbored subsurface oceans, could they still retain pockets of liquid water beneath their icy crusts? The implications for astrobiology are tantalizing, as such environments are considered potential havens for microbial life. Uranus in the spotlight, the future of exploration. Despite its wealth of mysteries, Uranus remains one of the least explored planets in the solar system. The only spacecraft to visit was Voyager 2, which flew by in 1986, capturing a fleeting glimpse of the planet and its moons. Since then, advances in technology and scientific understanding have made Uranus a prime target for future missions. Proposals for dedicated missions to Uranus have gained traction in recent years. These missions aim to deploy orbiters and atmospheric probes that could study the planet's interior, magnetic field, and atmosphere in unprecedented detail. By doing so, scientists hope to unravel the mysteries of Uranus formation, its unusual tilt, and its role in the broader context of planetary science. One particularly ambitious idea involves sending a spacecraft to explore Uranus moons, searching for signs of subsurface oceans and potential habitability. Such a mission could provide crucial insights into the icy worlds that populate the outer solar system, shedding light on the conditions necessary for life beyond Earth. The next steps in exploring Uranus promise to revolutionize our understanding of this distant world. But the deeper we probe, the more questions we are likely to uncover. Are you ready to continue unraveling the secrets of Uranus? The unseen depths. What lies beneath Uranus' atmosphere? While Uranus' atmosphere holds many mysteries, the planet's deeper layers remain even more elusive. Scientists suspect that beneath the icy exterior lies a dense, high-pressure ocean of superionic water, a state of matter where water molecules break apart and hydrogen ions flow like a liquid while oxygen forms a rigid lattice. This exotic form of water is thought to exist due to the immense pressures and temperatures within Uranus, creating conditions unlike anything found on Earth. This superionic ocean could play a crucial role in Uranus' chaotic magnetic field, as the movement of charged particles within this layer may generate the field's unique characteristics. But questions remain. How thick is this layer? Does it extend all the way to the planet's rocky core, or is there another phase of matter in between? To answer these questions, scientists need detailed measurements of Uranus' gravity and magnetic field, which could be provided by future spacecraft. By studying how the planet's magnetic field shifts over time, researchers could map the structure of its interior and uncover the processes shaping its evolution. The rings of Uranus, dynamic and evolving structures. While Saturn's rings are a well-known spectacle, Uranus' rings are equally intriguing in their subtlety and complexity. They are faint, dark, and composed of microscopic particles interspersed with larger chunks of material. This composition raises questions about their origin. Were they formed from a shattered moon, the remnants of a passing comet, or leftover material from Uranus formation? The rings are also remarkably narrow and sharply defined, a feature that puzzles scientists. Gravitational interactions with small shepherd moons are thought to confine the rings, preventing their particles from spreading out. However, many of these shepherd moons have yet to be identified, leaving gaps in our understanding of the system's dynamics. Recent studies suggest that Uranus rings may be younger than the planet itself, possibly forming within the last few 100 million years. If this is true, it implies that the rings are part of an ongoing process of destruction and renewal, shaped by collisions and gravitational forces. Exploring these delicate structures could reveal the story of how Uranus' ring system came to be and how it continues to evolve. Aurora mysteries, dancing lights in the cold darkness. Auroras, the ethereal light shows caused by charged particles interacting with a planet's magnetic field, are not unique to Earth. Uranus also hosts auroras, but they differ dramatically from those of other planets. Unlike Earth's auroras, which are concentrated around the magnetic poles, Uranus auroras can appear in unexpected locations, reflecting the planet's wildly tilted and offset magnetic field. These auroras are faint and difficult to observe, but they hold valuable clues about Uranus' magnetosphere and its interaction with the solar wind. Scientists have detected radio emissions from Uranus that are thought to be linked to these auroras, providing a rare glimpse into the planet's magnetic environment. Understanding Uranus auroras could also have broader implications for exoplanet research. Many exoplanets are thought to have magnetic fields and auroras, and studying Uranus may provide a template for interpreting the behavior of these distant worlds. The search for hidden oceans on Uranus moons. The possibility of subsurface oceans on Uranus moons is one of the most exciting prospects for future exploration. Moons like Titania, Oberon, and Ariel exhibit surface features that suggest geological activity, such as fractures and ridges, which could be linked to the movement of liquid water beneath their icy crusts. If these moons harbor oceans, they could be similar to those on Europa and Enceladus, where heat generated by tidal forces prevents the water from freezing solid. The presence of salts, organic molecules, and other chemicals in these oceans could create an environment suitable for life. Detecting these hidden oceans would require advanced instruments capable of penetrating the moon's icy shells. Radar, spectrometry, and magnetometry could provide the data needed to confirm their existence. If successful, such discoveries would transform our understanding of the potential for life in the outer solar system. How Uranus shapes the solar system. Despite its distance from the Sun, Uranus exerts a significant influence on the solar system. Its gravity affects the orbits of nearby objects, including the Kuiper Belt, a region of icy bodies beyond Neptune. Uranus' tilted axis and unusual orbit may also provide insights into the dynamics of planetary systems, helping astronomers understand how planets form and evolve. Uranus' impact extends beyond its immediate surroundings. By studying Uranus, scientists can refine their models of exoplanetary systems, particularly those containing ice giants. Many of the exoplanets discovered so far fall into the category of mini-Neptunes or super-Earths, which share similarities with Uranus in size and composition. Understanding Uranus' properties can therefore inform the search for habitable worlds in distant star systems. The call for a mission: why Uranus deserves more attention. Given its scientific importance, the lack of detailed exploration of Uranus is a glaring gap in our understanding of the solar system. A dedicated mission to Uranus could answer some of the most pressing questions about its tilt, magnetic field, interior structure, and potential habitability of its moons. Proposals for such a mission often include an orbiter and atmospheric probe. The orbiter could map Uranus' magnetic field and study its moons and rings, while the probe could dive into the atmosphere to analyze its composition directly. With advancements in technology, a mission to Uranus could achieve levels of precision and detail unimaginable during the Voyager era. The challenges of exploring Uranus are significant, given its distance from Earth and harsh conditions. But the rewards could be transformative, not only for our knowledge of Uranus, but for our understanding of planetary systems as a whole. Are we ready to commit to such an ambitious endeavor? The mysteries of Uranus await, and the next chapter of its story is ours to write. Unraveling the enigma of Uranus' tilted moons. The unique tilt of Uranus doesn't just affect the planet, it profoundly impacts its moons. Unlike the moons of other planets, which orbit around an upright axis, Uranus moons follow the planet's extreme inclination, resulting in a bizarre seasonal dance. For 42 years, one hemisphere of a moon faces continuous sunlight while the other is plunged into prolonged darkness. Then, the cycle reverses. This unusual alignment has consequences for the moon's surfaces and interiors. The constant bombardment of sunlight on one side and the freezing cold on the other creates temperature imbalances that might drive surface processes, such as the movement of volatile ices or the development of frost patterns. Could these temperature swings trigger sublimation or even limited geological activity? One of the most perplexing questions involves the stability of these moons. How did they form and align with Uranus' tilted axis? Did they coalesce from the same impact that may have caused Uranus tilt, or were they captured later? The answers to these questions hold the key to understanding the broader dynamics of Uranus' system. The hidden role of methane in Uranus evolution. Methane is one of the defining components of Uranus' atmosphere, giving the planet its striking blue-green color. But methane's role goes far beyond aesthetics. It offers clues about the planet's formation and atmospheric dynamics. Methane absorbs red light, masking the presence of other atmospheric components and complicating efforts to study Uranus in detail. However, researchers believe that beneath the methane-rich upper atmosphere lies a complex interplay of gases and ices, including hydrogen, helium, ammonia, and possibly hydrocarbons like ethane and acetylene. These compounds could reveal important details about Uranus' early environment. For example, the abundance of methane compared to other gases suggests that Uranus formed in a region rich in volatiles, likely in the cold outer reaches of the protoplanetary disk. Understanding how these elements are distributed within Uranus could also shed light on the processes that drive atmospheric circulation and chemistry. Recent observations using advanced telescopes have begun to uncover subtle variations in the methane content of Uranus' atmosphere, hinting at underlying dynamics. Could these variations point to upwelling currents or hidden storms? The answers may lie in the unseen depths of the planet. The energy puzzle. Why Uranus lacks heat? Uranus defies expectations with its lack of internal heat. Most planets, including Neptune, radiate more energy than they receive from the Sun due to the residual heat left over from their formation. Uranus, however, radiates almost no excess heat, making it an outlier among the giant planets. Several theories attempt to explain this anomaly. One possibility is that the hypothesized collision that tipped Uranus onto its side also disrupted its internal structure, allowing much of its primordial heat to escape. If true, Uranus' cold interior would be a relic of a violent past. Another theory involves the insulating effect of its thick, icy mantle. If this layer is particularly efficient at trapping heat, it could prevent the planet's interior from radiating outward. Alternatively, Uranus' atmosphere might lack the convective activity seen on other planets, which helps to transport heat to the surface. Solving this energy puzzle is essential for understanding not only Uranus but also ice giants in general. If similar processes occur on exoplanets, they could significantly impact their climates and potential habitability. Uranus and Neptune, twin planets with diverging fates. Uranus and Neptune are often referred to as twin planets because of their similar sizes and compositions, yet they display striking differences. While Neptune boasts a more dynamic atmosphere with visible storms and bands, Uranus appears much more subdued. What accounts for these disparities? One possibility is the difference in their internal heat. Neptune radiates significantly more energy than Uranus, which likely fuels its more active weather systems. This contrast might stem from variations in their formation histories or the distribution of materials in their interiors. Their magnetic fields also differ in both alignment and intensity. While Uranus' magnetic field is tilted and chaotic, Neptune's is slightly less extreme. These differences could reflect variations in the composition and behavior of the conductive layers within each planet. By comparing Uranus and Neptune, scientists hope to piece together a broader picture of how ice giants form and evolve. Could their differences be the result of chance, or do they reflect fundamental processes that operate across the universe? The future of Uranian exploration. As the scientific community looks ahead, Uranus is emerging as a priority for exploration. Its unique combination of features, extreme tilt, chaotic magnetic field, icy composition, and intriguing moons, makes it a compelling target for a flagship mission. Such a mission could answer fundamental questions not just about Uranus but about the nature of planetary systems as a whole. Key objectives for a Uranus mission would include mapping the interior, using gravity and magnetic field data to reveal the planet's internal structure, atmospheric probes, deploying instruments to study the composition, temperature, and dynamics of Uranus' atmosphere, ring studies, capturing high-resolution images and data on the composition and behavior of Uranus rings, moon exploration, investigating the geology and potential habitability of Uranus' largest moons, particularly Miranda, Ariel, and Titania, magnetosphere analysis, studying Uranus' magnetic field and its interaction with the solar wind. Such a mission would require advanced technologies, including long-duration power systems and high-precision instruments capable of operating in the harsh environment of the outer solar system. International collaboration could help make this ambitious endeavor a reality. The mysteries of Uranus are not just scientific curiosities. They are a window into the processes that shape planetary systems across the universe. By exploring Uranus, we are not only seeking to understand one of the most enigmatic worlds in our solar system, but also laying the groundwork for discoveries that could transform our knowledge of the cosmos. Are you ready to explore the uncharted depths of this icy giant? The story of Uranus is deeply intertwined with the evolution of the solar system itself. Each facet of this distant planet, from its peculiar tilt to its icy moons, reflects the chaotic and dynamic processes that shaped the early stages of planetary formation. The presence of such an extreme axial tilt continues to inspire theories about violent collisions or gravitational interactions that may have occurred billions of years ago. Yet, these theories remain incomplete, unable to fully explain the consequences of such a dramatic event on the planet's orbit, internal composition, and its magnetic field. Beneath the pale, featureless atmosphere of Uranus lies an interior that likely holds many answers. The icy layers that dominate the planet's composition are thought to behave in ways that defy conventional expectations. At the immense pressures found within Uranus, water, ammonia, and methane take on exotic forms, transitioning into superionic states or forming conductive fluids that might generate the planet's erratic magnetic field. This magnetic field, which behaves nothing like Earth's orderly dipole, is tilted and offset, creating interactions with the solar wind that remain poorly understood. It offers a window into the unique dynamics of ice giant interiors, which are likely mirrored on exoplanets throughout the galaxy. The moons orbiting Uranus are another enigma, their surfaces marked by deep scars and unusual terrains. Miranda, with its towering cliffs and chaotic features, stands out as a geological oddity. The forces that created these structures remain speculative, but the evidence of intense resurfacing suggests that these moons experienced internal heating in the past. Such heating may have been driven by tidal forces exerted by Uranus, which, despite its distance from the Sun, still wields powerful gravitational influence over its moons and rings. Ariel and Titania also show signs of past activity, with cracks and ridges that hint at the movement of subsurface liquids. The idea that some of these moons may still host hidden oceans, shielded beneath their icy crusts, adds another layer of intrigue. These oceans, if they exist, could be reservoirs of chemical complexity, possibly harboring conditions that resemble the precursors to life. The dynamic interactions between Uranus and its ring system are yet another aspect of the planet that captivates researchers. Unlike the wide, brilliant rings of Saturn, the rings of Uranus are narrow and dark, composed of material that reflects little light. Their sharp edges and defined structures suggest the influence of shepherd moons, small bodies whose gravitational pull confines the particles within the rings. The origin of these rings, however, remains a topic of debate. They could be remnants of a moon shattered by a collision or material left over from the planet's formation. Studying their composition and behavior might provide insights into the processes that govern ring systems around planets, both in our solar system and beyond. Uranus' lack of excess heat continues to puzzle scientists. Other giant planets radiate energy from their interiors, but Uranus emits only what it receives from the Sun. This anomaly suggests that something in Uranus' history or internal structure prevented it from retaining or releasing heat as expected. If the hypothesized collision that tilted Uranus also stripped away much of its primordial heat, this would explain its current thermal state. Alternatively, the planet's thick, icy mantle might act as an insulating layer, trapping heat within its core. Understanding this phenomenon could shed light on how ice giants differ from gas giants like Jupiter and Saturn. Despite being one of the most distant planets, Uranus holds a key to understanding not just our solar system, but the broader universe. Many exoplanets discovered orbiting other stars resemble ice giants like Uranus and Neptune. By studying these planets in detail, we gain a framework for interpreting the characteristics of similar worlds far beyond our reach. Uranus, with its tilt, icy composition, and chaotic magnetic field, serves as a natural laboratory for testing theories about planet formation and evolution. The planet's distance and faintness have left it largely unexplored, with only a brief flyby by Voyager 2 offering a glimpse of its features. However, this gap in our knowledge presents an incredible opportunity. A dedicated mission to Uranus could transform our understanding of ice giants and the broader processes that govern planetary systems. Such a mission would face significant challenges, requiring advanced propulsion and energy systems to operate at such a vast distance from the Sun. But the potential rewards, unraveling the mysteries of a planet that defies expectations, make the effort worthwhile. Every question about Uranus seems to lead to another, creating an endless chain of mysteries waiting to be solved. From its bizarre tilt to its faint rings, from its icy mantle to its chaotic moons, Uranus challenges the limits of our understanding and invites us to look deeper. Each discovery has the potential to reshape our perspective, not just of this planet, but of planetary science as a whole. The journey to uncover Uranus' secrets is far from over, and the next steps promise to bring us closer to answers that could redefine our place in the cosmos. Are we prepared to take that next leap into the unknown? The mysteries of Uranus await, and they are more compelling than ever. The allure of Uranus lies not only in what we already know, but in the tantalizing gaps that remain unexplored. Its distant orbit, shrouded in dim sunlight, casts the planet as an enigmatic outlier, yet it beckons us with the promise of profound insights. To truly grasp its place in the solar system, we must delve into the threads that connect Uranus to the greater cosmic narrative. From its suspected violent past to its serene, frigid present, Uranus embodies the duality of chaos and order that defines the universe itself. Its moons whisper stories of upheaval. Miranda, with its towering Verona Rupees cliff, stands as a testament to cataclysmic reshaping. Theories suggest a dramatic past. Perhaps it was shattered and reassembled multiple times, its fragments fusing into the fractured surface we see today. These scars are not merely geological. They are records of dynamic forces that may have acted on all moons within the Uranian system. The interplay of tidal heating, orbital resonances, and the potential migration of the moons themselves could have driven the resurfacing seen on Ariel and the ancient, cratered plains of Oberon. A deeper mystery lies in the possibility of oceans locked beneath the icy exteriors of these moons. The faint spectral hints of salts and other compounds suggest that chemical interactions occur even in these frozen realms. Could such processes, influenced by the lingering heat of tidal flexing or radioactive decay, sustain environments where the building blocks of life might arise? The tantalizing parallels with the icy moons of Jupiter and Saturn make Uranus moons prime candidates for future exploration. Beyond the moons, Uranus rings weave a subtler tale. The particles composing these narrow bands may be remnants of a once larger moon destroyed by an impact or tidal forces. If these particles originated from such a catastrophic event, they carry within them the history of Uranus' gravitational power and the fragility of its surroundings. The dynamics of these rings, shaped by gravitational shepherding and the occasional collision, mirror the delicate balancing act seen in ring systems across the solar system. The planet's magnetosphere adds yet another layer to its enigmatic nature. Unlike the symmetrical magnetic fields of Earth or Jupiter, Uranus' field is skewed and off-center, creating regions of unexpected intensity and strange auroras that dance irregularly across its atmosphere. These auroras, barely visible from Earth, reveal the interaction of charged particles streaming from the Sun with Uranus' chaotic magnetic shield. The behavior of this magnetosphere provides a model for understanding how similar fields might behave on distant exoplanets, many of which are expected to share Uranus' size and composition. Atmospherically, Uranus defies expectations. Its pale, almost featureless exterior hides immense forces at play. Winds reaching supersonic speeds circle the planet, while occasional storms, discovered only recently, hint at an underlying dynamism. Why such storms are less frequent than those observed on Neptune remains a puzzle. The temperature gradient, the sluggish convective motions within its atmosphere, or even subtle interactions with the planet's magnetic field might all contribute to this apparent calm. The methane that tints Uranus' atmosphere a blue-green hue is more than a cosmetic feature. It serves as both a clue and a mask, obscuring the deeper layers while hinting at the processes within. Methane's distribution, the presence of trace hydrocarbons, and the interplay between atmospheric layers all suggest a complex chemistry that may hold clues to the conditions of Uranus formation. The recent detection of hydrogen sulfide in the upper atmosphere adds another piece to this intricate puzzle, implying a primordial composition similar to that of icy bodies farther from the Sun. The puzzle of Uranus' coldness remains one of its greatest enigmas. While Neptune radiates significant heat left over from its formation, Uranus does not. Theories illuminate how similar disruptions influence planets and other systems. The potential for exploration of Uranus has never been greater. Advances in technology make it possible to design missions capable of enduring the long journey and the harsh conditions of the outer solar system. A spacecraft equipped with next-generation sensors could orbit the planet, deploying probes to dive into its atmosphere and study its composition, dynamics, and internal structure. Meanwhile, flybys of its moons could map their surfaces in detail, searching for signs of subsurface oceans and past geological activity. The challenges of such a mission are significant. Uranus lies at the edge of our technological reach, and its faint rings, dark moons, and subtle atmospheric features demand instruments of exceptional precision. However, the potential rewards far outweigh the difficulties. Each new discovery would deepen our understanding not only of Uranus, but also of the processes shaping ice giants and their systems across the cosmos. As we look to the future, Uranus stands as a reminder of how much we have yet to learn about our own cosmic neighborhood. Its serene appearance belies a history of upheaval and mystery, inviting us to probe its secrets. Each unanswered question beckons, each clue urging us onward. The journey to uncover Uranus' true nature is not just about understanding a single planet. It's about expanding the boundaries of human knowledge and exploring the fundamental forces that shape our universe. Are we ready to rise to the challenge and unlock the mysteries of this distant, tilted world? The adventure is only beginning. The enigma of Uranus persists, its mysteries acting as a cosmic puzzle that demands exploration and understanding. Despite its serene and almost featureless appearance, every aspect of this ice giant tells a story of complexity and contradiction. Its unique tilt, thought to be the result of a colossal collision, set Uranus apart as an outlier in the solar system. Yet, its stability in orbit and the survival of its moons and rings suggest that this dramatic event may have occurred early enough in its history to allow time for the system to reorganize itself into its current state. The planet's atmosphere, dominated by hydrogen, helium, and methane, gives it its iconic blue-green hue, but also conceals deeper secrets. Beneath the visible cloud tops lies a realm of intense pressure and temperature where exotic forms of matter may exist. The potential for superionic water, a state where water molecules break apart into freely moving hydrogen ions and rigid oxygen lattices, adds an entirely new layer to our understanding of planetary interiors. This unique composition could play a central role in Uranus' magnetic field, which defies traditional models with its chaotic, tilted, and off-center nature. As we peer deeper, the icy mantle surrounding Uranus' rocky core emerges as a crucial area of study. This mantle, composed primarily of water, ammonia, and methane in solid and fluid states, is believed to behave like a conductor under the planet's immense pressures. The interaction of these materials likely generates the magnetic field's erratic behavior, creating a system that challenges conventional understanding of planetary magnetodynamics. Further exploration could reveal how these processes might compare to those in other ice giants like Neptune or even exoplanets in distant star systems. The moons of Uranus continue to be a focal point of curiosity. Their diverse geologies, ranging from Miranda's jagged cliffs to Ariel's fractured plains, suggest that these satellites have experienced a range of geological processes. Some may have undergone cryovolcanism, where icy materials erupt onto the surface in a manner similar to volcanic activity on Earth. This resurfacing could point to internal heat sources driven by tidal forces, hinting at the presence of subsurface oceans. These hidden reservoirs, if they exist, could be dynamic environments where water interacts with minerals, potentially creating the conditions necessary for prebiotic chemistry. Rings encircle Uranus like faint whispers of its past. Unlike Saturn's luminous rings, those of Uranus are dark, narrow, and composed of fine particles mixed with larger fragments. The mechanisms that maintain these rings' sharp boundaries remain an active area of study, with gravitational shepherding by unseen moons as the leading explanation. However, the origin of the rings, whether they are remnants of a shattered moon, debris from a cometary impact, or relics of Uranus formation, remains an open question. Understanding these dynamics could provide broader insights into ring systems across the solar system and beyond. One of the planet's most enduring mysteries is its lack of internal heat. While Neptune, its twin in size and composition, radiates significant heat left over from its formation, Uranus appears almost thermally inert. This discrepancy raises fundamental questions about the energy budgets of ice giants and the processes that govern their thermal evolution. Was Uranus' heat dissipated during the hypothesized collision that tilted its axis, or is it trapped within its interior by an insulating layer? Investigating this anomaly could reshape our understanding of how planets retain and distribute energy over billions of years. Uranus also offers a unique perspective on the concept of seasons. With its axis tilted at 98 degrees, the planet experiences some of the most extreme seasonal changes in the solar system. For decades, one hemisphere faces continuous sunlight while the other remains in darkness. This prolonged exposure to light or shadow influences not only the atmosphere, but also the moons and rings, creating conditions that are vastly different from those on other planets. Observing these effects over time could provide valuable data on how extreme tilts impact planetary and satellite systems. The faint auroras of Uranus add yet another layer of intrigue. These shimmering lights, caused by the interaction of charged particles with the planet's magnetic field, are unlike the auroras seen on Earth or Jupiter. The tilted and offset nature of Uranus' magnetic field creates irregular patterns that challenge our understanding of magnetospheric physics. Studying these auroras could reveal how Uranus interacts with the solar wind and how such processes might manifest on similar exoplanets. The importance of Uranus extends far beyond our solar system. Many of the exoplanets discovered so far are classified as ice giants or share characteristics with Uranus in terms of size and composition. Understanding the internal dynamics, atmospheric processes, and magnetic phenomena of Uranus provides a foundation for interpreting data from these distant worlds. The similarities and differences between Uranus and exoplanets could reveal universal principles of planetary evolution while highlighting the diversity of planetary systems across the cosmos. Despite its significance, Uranus remains one of the least explored planets. The fleeting visit of Voyager 2 in 1986 provided invaluable data, but it barely scratched the surface of what this world has to offer. A dedicated mission to Uranus would open a new chapter in planetary science, addressing questions about its formation, evolution, and current state. Such a mission could deploy orbiters and atmospheric probes to study the planet in unprecedented detail, while flybys of its moons could uncover their secrets and search for signs of subsurface oceans. The technological challenges of exploring Uranus are formidable. Its vast distance from Earth, faint light, and extreme cold demand innovative engineering solutions. Yet, these obstacles also make the prospect of such a mission all the more exciting. The rewards, solving long-standing mysteries, discovering new phenomena, and expanding our understanding of planetary systems, are immeasurable. Uranus is a world of paradoxes, a planet that defies expectations while holding the key to understanding the processes that shape the universe. As we continue to look outward, the call to explore this distant giant grows stronger, urging us to embrace the challenge and uncover the secrets of a world that remains, for now, just out of reach. The journey to Uranus promises to be as transformative as it is ambitious, offering a glimpse into the uncharted depths of both the solar system and the human spirit of discovery. The mysteries of Uranus remain like whispers from the distant edges of the solar system, beckoning us to explore deeper. Each unanswered question about this icy giant seems to point not only to its unique nature, but also to broader patterns and anomalies that challenge our understanding of planetary science. Uranus stands as a testament to how much we still have to learn about the forces that govern not only our own solar system, but planetary systems across the universe. The violent origin story of Uranus' extreme tilt continues to provoke debate. If a massive collision truly reshaped the planet billions of years ago, the details of that event remain locked away beneath its opaque atmosphere and icy mantle. The energy released in such an impact would have been catastrophic, potentially ejecting material into space that may have formed the moons or rings. Yet, Uranus moons and their stable orbits suggest that this event, while transformative, left behind a system that could reorganize into the stable configuration we see today. It's a paradox that begs for closer examination. How does a cataclysm leave such subtle traces behind? The planet's frigid temperature raises questions about the processes that dictate planetary heat retention and dissipation. If Uranus experienced such a violent past, how does that reconcile with its apparent lack of internal heat? Is its icy mantle acting as an insulator, trapping what little heat remains deep within? Or did the collision dissipate most of the energy, leaving it colder than any other giant planet? Studying these thermal dynamics might not only solve the mystery of Uranus, but also illuminate how energy moves through other planets, including Earth-like exoplanets in distant star systems. The planet's atmospheric composition hints at processes both ancient and ongoing. The methane that paints Uranus its signature blue-green color absorbs red light, but also masks the deeper layers of its atmosphere. Beneath the visible clouds lie pressures and temperatures sufficient to break apart molecules, leading to exotic chemical reactions. Methane itself may be undergoing transformation into complex hydrocarbons, which could explain the presence of faint spectral signatures of acetylene and ethane. These compounds are more than just curiosities. They serve as clues to the chemical pathways active in Uranus' atmosphere and provide a template for understanding similar atmospheres on ice giant exoplanets. Uranus moons remain one of its most tantalizing mysteries. Their surfaces, scarred by impact craters and geological upheavals, suggest stories of intense and varied histories. Miranda, with its chaotic terrain and towering cliffs, has long intrigued scientists with its paradoxical nature. It is both ancient, with features dating back billions of years, and strangely youthful, with regions that seem to have been resurfaced relatively recently. The forces responsible for this duality may lie beneath Miranda's surface, where tidal interactions with Uranus could generate enough heat to drive tectonic or cryovolcanic activity. Titania and Oberon, the largest moons of Uranus, also show signs of potential geological complexity. Bright streaks and fractures on their surfaces hint at internal processes that could have once driven material upward from hidden depths. If these moons harbor subsurface oceans, they might also host environments where organic chemistry could occur. The mere possibility of such hidden, life-friendly niches so far from the Sun adds an almost poetic layer to the exploration of Uranus, turning these icy moons into symbols of resilience and potential. The rings of Uranus, though less prominent than Saturn's, are equally fascinating in their subtlety. Their dark composition and narrow structure speak of a dynamic system constantly shaped by gravitational interactions. Each ring particle carries with it the history of its origin, whether from a shattered moon, cometary debris, or leftover material from Uranus formation. Observing how these particles move and interact could unlock secrets about the forces that maintain such precise configurations in a system defined by extreme axial tilt and chaotic magnetism. The planet's magnetosphere is a puzzle unto itself, unlike anything seen elsewhere in the solar system. Its irregular field, tilted drastically from the planet's rotation, creates a magnetospheric bubble that is lopsided and constantly shifting. This chaotic magnetic environment produces auroras that do not align with Uranus poles and interact unpredictably with the solar wind. Understanding this phenomenon is not just about Uranus. It also has implications for exoplanets with similar fields, especially those orbiting close to their stars, where magnetic interactions could drive atmospheric loss or strange weather patterns. Looking outward from Uranus, the planet's influence extends to the distant Kuiper belt, where its gravity subtly shapes the orbits of icy bodies and dwarf planets. These interactions hint at a larger story of how Uranus and Neptune may have migrated early in the solar system's history, scattering smaller objects and carving out the structure we observe today. This migration, if confirmed, could help explain the strange distribution of objects in the outer solar system, and even shed light on the origins of the mysterious planet 9 hypothesized to lurk in the farthest reaches of our cosmic neighborhood. The exploration of Uranus offers a unique opportunity to address some of the most profound questions in planetary science. A dedicated mission to this ice giant would not only focus on the planet itself, but also its moons, rings, and magnetosphere. Such a mission would revolutionize our understanding of how ice giants form, evolve, and interact with their surroundings. The potential for groundbreaking discoveries is immense, from uncovering the secrets of the planet's interior to finding evidence of active geology or even subsurface oceans on its moons. The challenges of reaching Uranus are formidable, but they are not insurmountable. Advances in propulsion, instrumentation, and energy systems make it feasible to send a spacecraft to this distant world. The journey, though long, would offer unprecedented opportunities for exploration, and the data returned would have far-reaching implications not just for understanding Uranus, but for refining our models of planetary systems as a whole. As we stand on the cusp of a new era in space exploration, Uranus serves as a reminder of the unknown. It is a world that defies expectations, a planet of contradictions and extremes that challenges our understanding at every turn. Its secrets, once uncovered, will not only reshape our knowledge of the solar system, but also inspire a deeper appreciation for the intricate forces that govern the cosmos. The call to explore Uranus is not just about solving its mysteries. It's about embracing the spirit of discovery that drives us to reach for the stars and beyond. The journey to this distant, tilted world promises to be one of the most rewarding endeavors in the history of space exploration. The deeper we dive into the mysteries of Uranus, the more it challenges our perceptions of planetary systems. Its unique characteristics, from its peculiar tilt to its faint and dark rings, present a tapestry of scientific puzzles waiting to be unraveled. Yet, Uranus is not just a destination for curiosity. It is a key to understanding the broader story of planetary evolution, a story that extends far beyond our solar system. The planet's tilt, perhaps its most defining feature, invites a closer examination of how violent interactions in the early solar system shaped its destiny. If a massive collision was responsible, the event would have not only tilted the planet, but also influenced its internal structure, magnetic field, and orbit. However, if gravitational interactions with other massive bodies played a role instead, it raises the question of how often such dynamics occur in other planetary systems. Either scenario places Uranus at the heart of a broader cosmic narrative, one where chaos and order intertwine to sculpt planetary landscapes. The story of Uranus' interior remains hidden beneath its thick layers of gas and ice. Scientists hypothesize that beneath the atmosphere lies an ocean of superionic water, a strange and exotic phase of matter that could only exist under the extreme pressures and temperatures found deep within ice giants. This ocean might be the birthplace of Uranus' chaotic magnetic field, as the movement of charged particles generates a field that is wildly tilted and offset from the planet's core. Understanding how this field behaves could illuminate the internal processes of Uranus and provide a framework for studying similar planets beyond our solar system. The moons orbiting Uranus, each with their own unique features, tell tales of a dynamic past. Miranda's jagged cliffs and chaotic terrain suggest that it was reshaped multiple times, potentially by tidal forces or even impacts that shattered and reassembled the moon. Ariel, with its bright fractures and possible cryovolcanic features, hints at an active interior that may have once allowed water or other liquids to emerge onto the surface. Titania and Oberon, the largest moons, show older surfaces but still hold the potential for subsurface oceans. These hidden seas, if confirmed, would make Uranus moons part of a growing list of celestial bodies that might harbor environments suitable for the chemical precursors of life. Uranus' ring system, while less dramatic than Saturn's, is no less intriguing. Its faint and dark rings are composed of material that reflects very little sunlight, making them difficult to observe. Their sharp edges and precise structures suggest the presence of small shepherd moons, which maintain the ring's shape through gravitational interactions. The origin of these rings remains a mystery. Were they formed from the debris of a destroyed moon, or are they remnants of material that never coalesced into a larger body? The ring's composition could also provide clues about the building blocks of Uranus itself, offering a glimpse into the primordial material that shaped the early solar system. The planet's magnetic field stands as one of its most confounding features. Unlike the orderly dipole fields of Earth or Jupiter, Uranus' magnetic field is tilted at an extreme angle and offset from the planet's center. This irregularity creates a magnetosphere that wobbles and shifts, producing auroras that appear in unexpected places. The interaction of this chaotic field with the solar wind generates unique phenomena that could serve as analogs for studying magnetic fields on exoplanets. Many of the ice giants discovered around other stars likely share similar features, and Uranus provides an invaluable opportunity to study these behaviors up close. Uranus' atmosphere, seemingly calm at first glance, hides ferocious winds that can reach speeds of up to 900 kilometers per hour, 560 miles per hour. These winds, confined to specific latitudes, hint at complex dynamics driven by the planet's rotation, atmospheric composition, and internal energy, or lack thereof. The discovery of transient storms on Uranus suggests that its atmosphere is more dynamic than previously thought, but the rarity and subtlety of these events make them difficult to study. The methane that dominates its upper atmosphere provides the blue-green color we see, but deeper layers likely contain a mix of other compounds, such as hydrogen sulfide and ammonia, which contribute to the planet's complex chemistry. One of the most profound mysteries of Uranus is its lack of excess heat. Most giant planets, including Neptune, radiate more energy than they receive from the Sun, a relic of the heat generated during their formation. Uranus, however, emits almost no extra heat, making it the coldest planet in the solar system. This anomaly challenges our understanding of planetary thermodynamics. Was Uranus' internal heat lost in the violent event that tilted its axis, or does its thick mantle of ices act as a barrier, preventing heat from escaping? The answers to these questions could reshape our understanding of how planets retain and lose energy over time. Uranus also offers a unique perspective on the role of extreme axial tilts in shaping planetary climates and systems. With its poles taking turns facing the Sun for decades at a time, the planet experiences seasons unlike any other. These prolonged periods of light and darkness affect not only the atmosphere, but also the moons and rings, creating a system that is both fascinating and challenging to study. Observing these seasonal changes over time could provide valuable insights into how extreme tilts impact planetary systems, both within our solar system and beyond. Despite the wealth of mysteries, Uranus remains one of the least explored planets in the solar system. The brief flyby of Voyager 2 in 1986 provided invaluable data, but left many questions unanswered. A dedicated mission to Uranus, equipped with modern technology, could revolutionize our understanding of this icy giant. Such a mission might include an orbiter to study the planet's atmosphere, rings, and magnetic field, as well as flybys or landers to explore its moons. The potential for groundbreaking discoveries, whether about the planet's origins, its internal dynamics, or the habitability of its moons, makes Uranus a priority target for future exploration. The challenges of reaching Uranus are immense, but they pale in comparison to the potential rewards. Every mystery solved, every discovery made, would add a new layer to our understanding of planetary systems and the forces that shape them. Uranus is more than just a planet. It is a gateway to understanding the icy worlds that populate the universe, a category of planets that may be among the most common in the galaxy. By exploring Uranus, we not only unlock its secrets, but also open the door to comprehending countless other worlds that share its characteristics. The journey to Uranus is not just a scientific endeavor. It is a testament to humanity's desire to explore, to push boundaries, and to seek answers to the unknown. As we stand on the threshold of this next great leap in space exploration, Uranus reminds us of the vastness of the cosmos and the endless possibilities it holds. Its mysteries beckon us to venture further, to dive deeper, and to embrace the wonder of discovery that defines our species. In unlocking the secrets of Uranus, we take another step toward understanding our place in the universe and the forces that connect us to the stars. The call to explore Uranus grows louder with each passing year, driven by its unparalleled potential to expand our understanding of the cosmos. Its mysteries weave a narrative of contrasts, tranquil appearances masking tumultuous histories, cold exteriors concealing exotic processes, and distant isolation paired with profound scientific significance. Uranus is not merely an object of fascination, but a keystone in deciphering the evolutionary pathways of ice giants and their kin scattered across the galaxy. At the heart of Uranus' intrigue lies its unique axial tilt, a stark deviation from the planetary norm. While most planets spin like tops relative to their orbital plane, Uranus rolls like a barrel, its poles alternately facing the Sun for decades. This configuration reshapes not only the planet's climate, but also the dynamics of its entire system. How does such an extreme tilt affect atmospheric circulation, the formation and behavior of its rings, and the tidal forces acting on its moons? These questions are not just relevant to Uranus. They offer a lens through which to study other tilted worlds, whether in our solar system or among the countless exoplanets we have discovered. The tilt also highlights the resilience of Uranus' system. If the tilt was indeed caused by a cataclysmic impact, the fact that its moons and rings continue to exist in their current configurations suggests a remarkable capacity for self-organization. The gravitational interplay between Uranus, its moons, and its rings creates a dynamic equilibrium that has persisted for billions of years. Studying this balance could provide insights into how gravitational forces shape and stabilize planetary systems over time. Beneath the calm, bluish haze of Uranus' atmosphere lies an environment of extremes. Methane dominates the upper layers, giving the planet its signature color. But deeper down, the atmosphere transitions into regions of crushing pressure and searing heat. In these hidden depths, exotic forms of matter, such as superionic water, might flow, their charged particles potentially generating the planet's erratic magnetic field. This interior ocean, if it exists, would represent a state of matter rarely encountered on Earth and could redefine our understanding of planetary interiors. The erratic nature of Uranus' magnetic field remains one of its most confounding features. Unlike the magnetic fields of Earth or Jupiter, which are aligned relatively closely with their rotational axes, Uranus' field is tilted and offset, creating a lopsided magnetosphere. This asymmetry produces a magnetic environment that interacts with the solar wind in unpredictable ways, generating auroras that flicker in unexpected locations. Understanding these processes is vital not only for decoding Uranus, but also for interpreting the magnetic behavior of other ice giants and exoplanets. The moons of Uranus stand as silent witnesses to the planet's history, each carrying a fragment of its story. Miranda's dramatic cliffs and chaotic terrain suggest a history of repeated disruption, possibly from tidal heating or massive impacts. Ariel and Titania display surface features that hint at internal activity, including cryovolcanism and tectonic shifts. These moons, with their icy exteriors and potential subsurface oceans, are not just geological curiosities. They are candidates in the search for extraterrestrial life. The possibility that liquid water, the essential ingredient for life as we know it, exists beneath their surfaces elevates their importance as targets for exploration. The rings of Uranus, though faint and narrow, hold secrets of their own. Their composition, dark, carbon-rich material, and sharp boundaries suggest a dynamic history shaped by collisions and gravitational forces. The presence of shepherd moons, which help confine the rings, hints at a delicate interplay of forces that maintain their structure. By studying these rings, scientists can gain insights into the processes that govern ring systems across the solar system, from Saturn's luminous bands to the tenuous rings of Neptune and beyond. One of the most profound challenges Uranus presents is its thermal paradox. Unlike its neighbor Neptune, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This anomaly raises fundamental questions about how planets form and retain heat. Was Uranus' internal heat dissipated in the violent event that tilted its axis? Or is its heat trapped beneath insulating layers of ice? Could its lack of internal energy be tied to differences in its formation environment or composition? Solving this mystery could reshape our understanding of how ice giants evolve over billions of years. Despite the planet's distance and faint appearance, advances in technology have brought Uranus within reach of detailed exploration. A dedicated mission could provide unparalleled insights into its atmosphere, interior, magnetic field, and moons. An orbiter equipped with high-resolution cameras, spectrometers, and magnetometers could map the planet and its surroundings in exquisite detail, while atmospheric probes could dive into its clouds to analyze their composition and dynamics. Flybys of its moons could reveal surface features, subsurface structures, and even the presence of hidden oceans. The scientific potential of such a mission extends far beyond Uranus itself. By studying this ice giant, we gain a template for understanding similar planets and other star systems. Ice giants are among the most common types of exoplanets discovered, and Uranus serves as a natural laboratory for exploring their properties. Its composition, magnetic field, and thermal dynamics offer clues to how these distant worlds might behave, what conditions they might harbor, and whether they could support life. The exploration of Uranus is not just about solving mysteries. It is about expanding the boundaries of human knowledge. Each question answered about this distant world has the potential to reveal new insights about the processes that shape our universe. Uranus reminds us that even in the coldest, most remote corners of the solar system, there is beauty, complexity, and the promise of discovery. As we look toward the future, the case for exploring Uranus becomes ever more compelling. Its secrets call to us, urging us to venture farther and think deeper. The journey to Uranus is not just a scientific endeavor. It is a testament to humanity's insatiable curiosity and our determination to understand the cosmos. It is a journey that will connect us to the stars, to the icy worlds of distant systems, and to the universal forces that bind us all. The exploration of Uranus represents a defining opportunity to bridge gaps in our understanding of the outer solar system, offering a unique perspective on planetary evolution, dynamic systems, and the potential for life in unexpected places. Its allure lies not only in its mysteries, but in the profound questions it poses about the mechanisms that govern our solar system and beyond. The planet's moons, frozen yet dynamic, remain a key focus for future investigation. Each one carries the potential to rewrite what we know about icy satellites and their hidden complexities. Miranda, with its colossal canyons and stark contrasts, continues to baffle scientists with its evidence of extreme resurfacing. The moon's jagged landscapes, possibly caused by repeated tidal stresses, hint at a tumultuous past. These forces, driven by gravitational interactions with Uranus, could still be active beneath its surface, generating heat and perhaps sustaining a subsurface ocean. Such an environment, isolated and shielded from the harshness of space, may harbor the chemical ingredients for life. Titania and Oberon, the largest moons, may offer subtler but equally compelling stories. Both exhibit signs of ancient geological activity. Fractures and rifts across their icy crust suggest that internal processes once shaped their surfaces. If subsurface oceans remain beneath these moons, kept liquid by residual heat or the faint tug of tidal forces, they too could be havens for complex chemistry. The detection of even the faintest hints of organic molecules or heat signatures on these moons would revolutionize our understanding of life's potential habitats. Ariel, another of Uranus' major moons, shows evidence of relatively young geological features, such as valleys and smooth plains that may have been formed by cryovolcanism. This suggests that the moon experienced significant internal heat in its past, potentially fueled by tidal interactions or radioactive decay. Studying these surface features closely could reveal whether Ariel remains active today or if it has cooled into a geologically dormant state. In either case, it provides yet another piece of the puzzle in understanding the diversity of Uranus' satellite system. The planet's rings, though less prominent than those of Saturn, hold secrets about their origins and the forces that sustain them. The dark, carbonaceous material in the rings points to a history of destruction, perhaps the remnants of a moon shattered by an impact or the fragments of a captured object torn apart by Uranus' gravity. The sharp boundaries of the rings, maintained by the gravitational influence of tiny shepherd moons, reflect an intricate balance between order and chaos. Investigating these dynamics could provide new insights into how ring systems evolve and interact with their environments. Beneath Uranus' atmospheric veil lies a world defined by extremes. The serene, bluish hue hides powerful winds that race across its surface at speeds unmatched by any storm on Earth. These winds, driven not by solar energy, but by the planet's rotation and internal dynamics, create a banded structure that can only be seen in the infrared spectrum. Occasionally, bright storms appear, revealing the dynamic processes within Uranus' atmosphere. The triggers for these storms remain unclear, but they suggest that Uranus is far from the static world it once seemed. The chemistry of Uranus' atmosphere continues to intrigue researchers. Methane, which dominates the upper layers, plays a dual role as both a tracer of atmospheric motion and a mask that obscures deeper layers. Beneath the methane haze, a mixture of hydrogen sulfide, ammonia, and other trace compounds might tell the story of the planet's formation and evolution. Analyzing these elements could reveal how Uranus assembled its icy mantle and whether its current state reflects primordial conditions or subsequent alterations. One of the most compelling mysteries of Uranus is its energy deficit. Unlike Neptune, which radiates more energy than it receives from the sun, Uranus appears almost thermally inert. This anomaly could be the result of an ancient impact that disrupted the planet's internal structure, allowing its heat to escape into space. Alternatively, Uranus' interior might be uniquely stratified, with a thick, icy mantle that insulates the core and prevents heat from reaching the surface. Resolving this mystery would have profound implications for understanding the thermal evolution of not only Uranus, but also similar planets in distant systems. The magnetic field of Uranus is another enigma. Its dramatic tilt and offset from the planet's center create a lopsided magnetosphere that behaves unpredictably. The field's asymmetry generates unique auroras and interacts with the solar wind in ways that challenge existing models of planetary magnetism. By studying this field in detail, scientists could uncover the processes that drive its irregular behavior and apply these findings to other planets with unusual magnetic configurations. Despite its many mysteries, Uranus remains one of the least explored planets in the solar system. The Voyager 2 flyby provided invaluable data, but only scratched the surface of what this ice giant has to offer. A dedicated mission to Uranus, equipped with state-of-the-art instruments, could transform our understanding of this world. An orbiter could map the planet's magnetic field, analyze its atmospheric composition, and capture high-resolution images of its moons and rings. Atmospheric probes could descend into Uranus clouds to study their dynamics and chemistry directly. Such a mission would address not only the questions posed by Uranus, but also broader issues in planetary science, such as the nature of ice giants and their role in shaping planetary systems. The importance of Uranus extends far beyond the boundaries of our solar system. Many of the exoplanets discovered to date are classified as ice giants or share characteristics with Uranus and Neptune. By studying these planets up close, we gain a deeper understanding of their atmospheres, compositions, and magnetic fields, which can be used to interpret data from distant worlds. Uranus serves as a Rosetta Stone for unlocking the secrets of similar planets scattered throughout the galaxy. The drive to explore Uranus is more than a scientific endeavor. It is a testament to humanity's insatiable curiosity and our desire to push the boundaries of knowledge. Its mysteries remind us of the vastness of the cosmos and the infinite possibilities it holds. Uranus challenges us to look beyond what is familiar and embrace the unknown, venturing into the farthest reaches of our solar system in search of answers. The journey to Uranus is not just about uncovering the secrets of one planet. It is about broadening our horizons and deepening our understanding of the universe. Each discovery made on this distant world brings us closer to understanding the forces that shaped our solar system and the countless others like it. Uranus stands as a beacon of exploration, a reminder of the beauty and complexity that lie beyond our reach, waiting to be discovered. In unraveling its mysteries, we take another step toward answering the age-old question of humanity's place in the cosmos. The exploration of Uranus promises to be a transformative chapter in humanity's quest to understand the universe. Its cold, distant demeanor masks a vibrant system rich in complexity, where physics, chemistry, and geology collide in ways that challenge existing theories. Every corner of this enigmatic world, from its tilted axis to its chaotic magnetic field, from its moons with their fractured surfaces to its faint, mysterious rings, beckons with unanswered questions and the promise of discovery. The planet's history is etched into its structure. Its extreme axial tilt, likely the result of a massive collision during its formation, sets it apart from all other planets. This tilt not only reshaped Uranus itself, but likely influenced the dynamics of its moons and rings. The event may have scattered debris that formed the rings, perturbed the orbits of its satellites, or even altered the distribution of materials within the planet's interior. Yet the precise details of this ancient cataclysm remain shrouded in mystery, offering a tantalizing puzzle that scientists are eager to solve. The potential for exotic matter deep within Uranus adds another layer to its intrigue. The immense pressures and temperatures found in the planet's interior could create forms of matter rarely encountered elsewhere in the solar system. Superionic water, where hydrogen ions move freely through a rigid lattice of oxygen atoms, might exist in the planet's icy mantle, contributing to its magnetic anomalies. Such a state of matter could also play a role in the generation of Uranus' chaotic magnetic field, which defies traditional models with its tilted, off-center configuration. Understanding this field could provide valuable insights into the behavior of magnetic fields on other planets, including Earth-like worlds and distant star systems. The moons of Uranus, though smaller and less studied than the major satellites of Jupiter and Saturn, are no less fascinating. Each one offers a unique window into the processes that shape icy worlds. Miranda's towering cliffs and jumbled terrain speak of a history marked by upheaval and renewal, while Ariel's smooth plains and fractured crusts suggest more recent geological activity. Titania and Oberon, with their ancient surfaces and potential for hidden oceans, present opportunities to explore the conditions necessary for sustaining liquid water far from the sun. These moons are not merely geological curiosities. They could also hold clues to the potential for life in the outer solar system. Subsurface oceans, if they exist, might be kept warm by tidal heating or radioactive decay, creating environments where water, heat, and chemical nutrients combine. Such conditions are among the most promising for prebiotic chemistry, the precursor to life as we know it. Discovering even the faintest signs of these processes on Uranus moons would have profound implications for our understanding of habitability beyond Earth. The rings of Uranus, faint and elusive, are another key to unlocking the planet's secrets. Their dark, carbon-rich material and sharp boundaries point to a dynamic history shaped by collisions, gravitational interactions, and perhaps the ongoing influence of shepherd moons. The structure and composition of these rings could provide insights into the formation and evolution of similar systems, from the dramatic rings of Saturn to the barely visible arcs of Neptune. Uranus' atmosphere, with its subdued appearance, hides one of the most extreme environments in the solar system. Winds reach supersonic speeds, yet their patterns are less distinct than those on other planets, suggesting that deeper processes may play a significant role in driving atmospheric circulation. Occasional storms, detected through infrared observations, hint at a level of dynamism that defies the planet's otherwise calm exterior. The atmosphere's composition, dominated by hydrogen, helium, and methane, reflects the primordial material from which the planet formed, offering a window into the conditions of the early solar system. The planet's lack of significant internal heat remains one of its most perplexing mysteries. Unlike Neptune, which radiates more energy than it receives from the sun, Uranus emits almost no excess heat. This anomaly could be tied to its violent past. Perhaps the collision that tilted its axis also ejected much of its internal energy into space. Alternatively, the planet's internal structure may include layers that act as thermal barriers, preventing heat from escaping. Solving this puzzle is essential for understanding not only Uranus, but also the thermal evolution of planets in general. The study of Uranus is not just about understanding one planet. It is about piecing together the larger story of the solar system's formation and evolution. Uranus occupies a unique position in this narrative, serving as a bridge between the inner, rocky planets and the more massive gas giants. Its composition, dominated by ices rather than hydrogen and helium, offers clues about the distribution of materials in the protoplanetary disk. By studying Uranus, we can refine our models of planetary formation and gain insights into how similar planets might form in other star systems. Future missions to Uranus hold the promise of transformative discoveries. Advances in spacecraft technology, including more efficient propulsion systems and durable instrumentation, make it feasible to reach the planet and conduct in-depth studies. An orbiter could map its magnetic field, analyze its atmosphere, and capture high-resolution images of its moons and rings. Probes could descend into its atmosphere, measuring temperature, pressure, and chemical composition as they plunge through the clouds. Flybys of the moons could reveal surface features, search for signs of geological activity, and detect subsurface oceans. The significance of Uranus extends far beyond the solar system. Many of the exoplanets discovered so far are classified as ice giants or share characteristics with Uranus. By studying this planet, we gain a framework for interpreting data from these distant worlds, understanding their atmospheres, and assessing their potential habitability. Uranus serves as a natural laboratory for exploring the properties and behaviors of planets that are among the most common in the galaxy. In the grand scheme of exploration, Uranus challenges us to think bigger, to venture farther, and to embrace the unknown. Its mysteries are a testament to the complexity and diversity of the universe, reminding us that even in the coldest and most remote corners of the solar system, there is still much to learn. The journey to uncover Uranus' secrets is not just a scientific endeavor. It is a celebration of humanity's relentless curiosity and our unyielding drive to understand the cosmos. As we prepare for the next era of space exploration, Uranus stands as a beacon of discovery, a world that defies expectations and invites us to explore its depths. The answers it holds could reshape our understanding of the solar system, inspire future generations of scientists and explorers, and deepen our connection to the universe. The call to Uranus is clear, and the time to answer it is now. The journey promises to be challenging, but the rewards, a deeper understanding of our place in the cosmos, will be immeasurable. The journey to Uranus represents not just a step forward in planetary exploration, but a monumental leap in our understanding of the universe's icy giants, both near and far. Its unique attributes and dynamic system provide a treasure trove of scientific questions that span disciplines, from astrophysics and planetary geology to atmospheric chemistry and the search for life. Each facet of Uranus, its rings, moons, atmosphere, magnetic field, and internal structure, offers a piece of a larger puzzle, one that could redefine our knowledge of planetary systems as a whole. The question of Uranus rings remains central to understanding its history and dynamics. Unlike the bright, expansive rings of Saturn, Uranus rings are subtle, almost spectral in their appearance, composed of dark, carbonaceous material. Their narrow, sharply defined edges suggest ongoing interactions with unseen shepherd moons, whose gravitational forces sculpt the rings into precise structures. What makes these rings even more enigmatic is their apparent youth. Some models suggest that they may have formed only a few 100 million years ago, perhaps as a result of a catastrophic collision that shattered a moon or other icy body. Investigating the composition, origin, and evolution of Uranus rings could provide critical insights into the life cycle of ring systems across the solar system. Its moons, too, hold a vital key to understanding Uranus' history and potential. Miranda, with its chaotic terrain, deep canyons, and stark contrasts, continues to fascinate scientists. Its surface appears to have been reworked multiple times, possibly through tidal heating driven by gravitational interactions with Uranus. This process may have generated enough internal energy to melt parts of Miranda's icy interior, leading to the upwelling and refreezing of material on its surface. Such processes may still be active today, raising the possibility of liquid water hidden beneath the crust. Ariel, with its evidence of cryovolcanism and relatively smooth plains, offers another potential site of interest for detecting subsurface activity. Could these moons, long thought to be lifeless and frozen, harbor dynamic environments where water and organic compounds interact? The potential for subsurface oceans on Uranus' larger moons, such as Titania and Oberon, adds another layer of intrigue. These moons exhibit ancient, cratered surfaces, but fractures and ridges suggest that internal processes once played a role in shaping their landscapes. If internal heat from radioactive decay or tidal forces persists, it might keep water in a liquid state beneath their icy exteriors. Such oceans would be shielded from the extreme cold and radiation of space, creating environments where prebiotic chemistry, or even life, could emerge. Detecting such oceans would not only reshape our understanding of these moons, but also expand the criteria for habitability in the outer solar system. The planet's magnetic field continues to defy conventional understanding. Uranus' magnetic poles are tilted dramatically relative to its rotation axis, and the field itself is offset from the planet's center. This irregularity creates a lopsided magnetosphere that interacts with the solar wind in unpredictable ways. Auroras flicker across the planet, but not at the poles as they do on Earth. Instead, they appear in unexpected regions, driven by the chaotic geometry of the magnetic field. Exploring this magnetosphere could yield new insights into how planetary magnetic fields are generated and how they evolve over time. Such knowledge could also inform studies of magnetic fields on exoplanets, where similar dynamics might play a role in shaping planetary atmospheres. Uranus' atmosphere, dominated by hydrogen, helium, and methane, hides a realm of extreme conditions and subtle variations. The methane absorbs red light, giving the planet its distinctive blue-green color, but it also masks deeper layers where more complex processes occur. Recent observations suggest the presence of trace amounts of hydrogen sulfide, adding to the complexity of the atmospheric chemistry. Beneath the visible cloud tops, temperatures and pressures rise dramatically, creating conditions where exotic chemical reactions and atmospheric dynamics unfold. The occasional appearance of storms and bright spots hints at internal processes driving weather patterns, but the mechanisms remain poorly understood. The absence of significant internal heat makes Uranus unique among the giant planets. Unlike Neptune, which radiates more energy than it receives from the Sun, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This anomaly could result from its unusual internal structure, where a thick layer of icy material may act as an insulator, trapping heat deep within. Alternatively, the violent collision that tilted Uranus on its side might have ejected much of its primordial heat into space. Understanding why Uranus lacks internal heat is not just a question about one planet. It has broader implications for how energy is retained and dissipated in planetary systems, both here and in other star systems. Future exploration of Uranus is not just an opportunity, it is a necessity. A dedicated mission to Uranus would provide answers to many of the questions that have lingered since Voyager 2's brief flyby in 1986. Modern spacecraft equipped with advanced instruments could study Uranus' atmosphere, magnetic field, rings, and moons in unprecedented detail. Probes could be sent into the planet's atmosphere to directly measure its composition and dynamics, while flybys of its moons could search for signs of subsurface oceans and active geology. An orbiter could map the magnetic field, analyze the ring system, and monitor seasonal changes in the atmosphere. The knowledge gained from such a mission would extend far beyond Uranus itself. Ice giants are among the most common types of planets found in other star systems, and Uranus serves as a natural laboratory for understanding their properties. By studying this distant world, we can refine models of planetary formation and evolution, explore the potential for life in icy environments, and gain insights into the diversity of planetary systems throughout the galaxy. The mysteries of Uranus remind us of the vastness of the cosmos and the uncharted territories that lie within our reach. They challenge us to think creatively, to push the boundaries of exploration, and to embrace the unknown. Each discovery made on Uranus, whether about its moons, rings, atmosphere, or interior, brings us closer to answering fundamental questions about our place in the universe. The journey to Uranus is not just a scientific endeavor. It is a testament to humanity's enduring curiosity and our unyielding drive to understand the cosmos. As we prepare for the next great leap in space exploration, Uranus stands as a beacon of possibility, a world that defies expectations and invites discovery. Its secrets await those who dare to explore, promising revelations that will reshape our understanding of the solar system and beyond. The call to Uranus is clear, and the adventure to unlock its mysteries will inspire generations to come, fueling the human spirit of exploration and connecting us to the stars. The call to explore Uranus is more than a scientific challenge. It is an invitation to push the boundaries of our understanding and expand the horizons of what we know about planetary systems. As a planet that defies conventional wisdom, Uranus offers a wealth of opportunities to uncover the processes that govern not only its own unique characteristics, but also the broader mechanisms shaping the cosmos. The planet's interior, shrouded in mystery, holds the keys to understanding its thermal and magnetic properties. Beneath its tranquil-looking atmosphere lies a realm of immense pressure and temperature, where exotic materials such as superionic water may flow. This state of matter, in which hydrogen ions move freely while oxygen atoms remain in a rigid structure, could explain the unusual tilt and offset of Uranus' magnetic field. If true, studying this phenomenon could shed light on similar conditions within other ice giants, both in our solar system and among the exoplanets we have discovered. The peculiarities of Uranus' magnetic field also raise questions about how planetary magnetospheres interact with their environments. The irregular geometry of Uranus' field creates a magnetosphere that is constantly changing as it rotates. This dynamic environment affects how the solar wind interacts with the planet, generating auroras in unexpected locations. By studying these interactions, scientists could gain insights into the behavior of magnetic fields under unusual conditions, with implications for understanding exoplanetary systems and even stellar magnetic fields. Uranus moons, each with its own unique story, provide further evidence of the planet's complex history. Miranda's jagged cliffs and chaotic terrain suggest repeated cycles of disruption and renewal, possibly driven by tidal forces exerted by Uranus. These forces could still be active today, generating heat within the moon's interior and potentially sustaining a subsurface ocean. Similarly, aerial smooth plains and fractured surface hint at past geological activity, while Titania and Oberon may harbor oceans beneath their icy crusts. If these oceans exist, they could be some of the most intriguing locations in the solar system to search for the chemical precursors of life. The faint, dark rings of Uranus offer yet another avenue for exploration. Their composition and structure suggest a dynamic past, possibly involving collisions that shattered moons or other icy bodies. These particles, confined by gravitational interactions with shepherd moons, reflect a delicate balance of forces that has persisted over time. Understanding the origins and evolution of these rings could provide clues about the processes that govern ring systems, from Saturn's majestic bands to the faint arcs of Neptune and even the rings of exoplanets. One of the most puzzling aspects of Uranus is its lack of internal heat. Unlike its neighbor Neptune, which radiates significantly more energy than it receives from the Sun, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This anomaly raises fundamental questions about the planet's formation and evolution. Was its heat lost in the cataclysmic event that tilted its axis, or is it trapped within its interior by a unique combination of materials? Exploring this mystery could provide a new understanding of how energy is stored and dissipated within planets, with implications for ice giants across the galaxy. The atmosphere of Uranus, while appearing calm, is anything but static. Supersonic winds, subtle banding, and occasional bright storms reveal a dynamic system influenced by both internal and external forces. Methane dominates the upper layers, absorbing red light and giving the planet its characteristic hue, but it also obscures deeper layers where more complex chemistry takes place. Recent observations suggest trace amounts of hydrogen sulfide, adding to the diversity of Uranus' atmospheric composition. Probing this atmosphere could uncover the processes driving its weather patterns and chemistry, offering a deeper understanding of ice giant atmospheres. A dedicated mission to Uranus would mark a new era in planetary exploration. An orbiter equipped with advanced instruments could map the planet's magnetic field, analyze its atmosphere, and observe its moons and rings over time. Probes could descend into the clouds to measure temperature, pressure, and chemical composition, while landers or flybys of the moons could search for geological activity and evidence of subsurface oceans. Such a mission would not only address fundamental questions about Uranus, but also provide a framework for studying similar planets in other star systems. The significance of Uranus extends far beyond its immediate environment. Ice giants are among the most common types of planets found in the galaxy, and Uranus offers a natural laboratory for understanding their properties. By studying Uranus, we can refine our models of planetary formation and evolution, explore the diversity of planetary atmospheres, and assess the potential for life in icy environments. The insights gained from Uranus will inform the search for habitable worlds beyond our solar system, guiding the next generation of astronomical discoveries. The exploration of Uranus is not just about solving scientific puzzles. It is about embracing the spirit of discovery that drives humanity to explore the unknown. Its mysteries remind us of the vastness of the universe and the infinite possibilities that lie beyond our reach. Each question answered about Uranus will open new avenues of inquiry, deepening our understanding of the cosmos and our place within it. As we look to the future, the case for exploring Uranus becomes ever more compelling. Its secrets await those bold enough to seek them, promising discoveries that will transform our understanding of the solar system and beyond. The journey to Uranus is not just a mission. It is a legacy, a testament to humanity's relentless curiosity and our determination to uncover the truths that lie hidden in the farthest corners of the universe. The call to Uranus is clear, and the time to answer it is now. Let us embrace this opportunity to explore, to discover, and to connect with the mysteries of a distant world that holds the keys to understanding the cosmos. The exploration of Uranus is not merely an endeavor to understand one distant world. It is a gateway to uncovering the fundamental principles that govern planetary systems throughout the cosmos. Its mysteries lie at the crossroads of science and discovery, challenging us to expand our knowledge and redefine our assumptions about the universe. Uranus invites us to explore not only its own enigmatic features, but also the broader questions about the formation, evolution, and diversity of planets, both in our solar system and among the stars. The unique axial tilt of Uranus, which causes it to spin almost horizontally relative to its orbit, is a striking anomaly that has captivated scientists for decades. This extreme inclination affects everything about the planet, from its seasons to its magnetic field, and likely traces back to a cataclysmic collision during the solar system's infancy. Such a violent event would have reshaped the planet's structure, scattered debris, and influenced the orbits of its moons and rings. Yet, the precise details of this ancient event remain elusive. Future exploration could reveal the scars left behind, hidden in the composition of the planet's atmosphere, the dynamics of its interior, or the arrangement of its satellites. Uranus moons offer an unparalleled opportunity to study the diversity and complexity of icy worlds. Each moon is a microcosm of geological activity and history. Miranda's surface, with its jagged cliffs and chaotic terrain, is a testament to intense tidal forces that may have once heated its interior. This heating could have driven cycles of melting and refreezing, creating the dramatic features we observe today. Ariel, with its evidence of cryovolcanism, suggests a similarly active past, while Titania and Oberon hint at the potential for hidden oceans beneath their icy crusts. If subsurface oceans exist, they could serve as laboratories for studying the interactions between water, heat, and organic chemistry, conditions that may lead to the emergence of life. The potential for life on Uranus moons elevates their significance as targets for exploration. Subsurface oceans, shielded from the harsh conditions of space, are environments where chemical reactions could thrive. The presence of organic compounds, combined with energy sources such as tidal heating or radioactive decay, could create the precursors for life. The detection of such conditions would not only transform our understanding of habitability, but also redefine our search for life beyond Earth. The rings of Uranus, though less prominent than Saturn's, are no less fascinating. Their dark, narrow structure and sharp boundaries suggest a dynamic history shaped by gravitational interactions and collisions. The material in these rings may be remnants of a shattered moon or other celestial body, providing a snapshot of the planet's past. Studying their composition and behavior could reveal how rings form, evolve, and interact with their environments, offering insights into similar systems around other planets and even exoplanets. Uranus' atmosphere, dominated by hydrogen, helium, and methane, hides a realm of complex chemistry and dynamic processes. The methane absorbs red light, giving the planet its iconic blue-green color, but it also conceals deeper layers where temperatures and pressures create conditions for exotic reactions. The occasional appearance of storms and bright spots suggests that the atmosphere is more active than it seems, driven by processes that remain poorly understood. Probing the atmosphere could uncover the mechanisms behind its weather patterns, trace its chemical evolution, and provide clues about the planet's origins. The lack of internal heat on Uranus remains one of its greatest mysteries. Unlike Neptune, which radiates significant energy left over from its formation, Uranus emits almost no excess heat, making it uniquely cold among the giant planets. This anomaly could be tied to the planet's internal structure, where a thick layer of ice may insulate the core and prevent heat from escaping. Alternatively, The violent event that tilted Uranus' axis may have expelled much of its internal energy into space. Understanding this thermal deficit could shed light on the energy dynamics of ice giants and their role in planetary evolution. Uranus' magnetic field, tilted and offset from the planet's center, is another anomaly that defies traditional models. This irregular field creates a lopsided magnetosphere that interacts unpredictably with the solar wind, producing auroras in unexpected locations. By studying the magnetic field in detail, scientists could uncover the processes that generate it and explore how magnetic fields influence planetary atmospheres and environments. These findings would also have implications for understanding exoplanetary systems, where magnetic fields play a critical role in shaping habitability. A mission to Uranus would be a monumental achievement, combining cutting-edge technology with the spirit of exploration. An orbiter equipped with advanced instruments could map the planet's magnetic field, analyze its atmosphere, and study its moons and rings in unprecedented detail. Probes could descend into the atmosphere to measure its composition, temperature, and pressure, while landers or flybys of the moons could search for signs of geological activity and subsurface oceans. The data gathered from such a mission would address fundamental questions about Uranus while advancing our understanding of ice giants and their role in the solar system. The insights gained from exploring Uranus would resonate far beyond its icy realm. Ice giants like Uranus and Neptune are among the most common types of planets discovered in other star systems. By studying Uranus, we gain a framework for interpreting data from these distant worlds, understanding their atmospheres, and assessing their potential for habitability. The discoveries made on Uranus could serve as a guide for future missions to explore exoplanets, bridging the gap between our solar system and the broader galaxy. The journey to Uranus is not just about unlocking its secrets. It is about embracing the unknown and expanding the boundaries of human knowledge. Its mysteries remind us of the infinite possibilities that lie beyond our reach, challenging us to think bigger and explore deeper. Each discovery brings us closer to understanding the forces that shape our universe and our place within it. As humanity stands on the brink of a new era in space exploration, Uranus serves as a beacon of discovery and a testament to our unyielding curiosity. The call to explore this distant world is a call to dream, to innovate, and to push the limits of what is possible. The answers hidden within Uranus' icy depths are waiting, and the journey to uncover them will inspire generations to come. It is a journey that connects us to the stars and to the shared wonder of exploring the unknown. Let us rise to the challenge and unlock the mysteries of Uranus, a world that holds the key to understanding the cosmos. As we set our sights on Uranus, the potential for discovery stretches far beyond the planet itself, reaching into the realms of astrophysics, planetary science, and the very origins of the solar system. Uranus is more than an enigmatic ice giant. It is a time capsule of ancient processes and a frontier for modern exploration. Its secrets are intertwined with the broader narrative of how planetary systems form, evolve, and sustain dynamic, complex interactions over billions of years. The axial tilt of Uranus, nearly perpendicular to the plane of its orbit, is a defining feature that demands deeper investigation. This tilt challenges traditional models of planetary motion and stability. If caused by a massive collision, it would have been a defining moment in the early solar system, scattering debris, redistributing energy, and reshaping the planet's structure. Alternatively, if the tilt resulted from gravitational interactions with neighboring giant planets or even an ancient rogue body, it underscores the delicate dance of celestial mechanics that governs planetary systems. Understanding this tilt could offer insights into the histories of exoplanets with similarly unusual configurations, many of which have been detected in recent years. The planet's internal structure remains one of its most compelling mysteries. Beneath its tranquil atmospheric layers lies a dense, icy mantle that is thought to consist of water, ammonia, and methane in exotic forms. These materials, subjected to the immense pressures and temperatures inside Uranus, may behave in ways that defy expectations. Superionic water, in particular, presents an exciting possibility, as it could explain the chaotic and asymmetric nature of the planet's magnetic field. Such insights could reshape our understanding of how magnetic fields are generated and sustained, not only on Uranus but on ice giants across the galaxy. Uranus moons, with their diverse features and histories, are treasure troves of geological and potentially astrobiological significance. Miranda's towering cliffs, some of the highest in the solar system, and its patchwork surface speak to a history of tidal heating and resurfacing. Ariel's fractured plains and cryovolcanic features hint at internal activity that may still be ongoing. Titania and Oberon, with their ancient surfaces, might conceal subsurface oceans, protected from the frigid vacuum of space by thick, icy shells. These oceans, if they exist, would be some of the most isolated and intriguing environments in the solar system, where water, energy, and organic molecules might combine to create the conditions necessary for life. The rings of Uranus, though faint and narrow, are no less captivating. Their composition, primarily dark, carbonaceous material, suggests a history of collisions and fragmentation. These rings may be remnants of a destroyed moon or a captured object that was torn apart by Uranus gravity. The precise mechanics that maintain their sharp boundaries, likely through interactions with shepherd moons, remain a topic of active research. Understanding these dynamics could provide valuable insights into the processes that shape and sustain ring systems, not just around Uranus but across the solar system and beyond. The atmosphere of Uranus, with its serene blue-green appearance, hides powerful dynamics beneath its calm exterior. Winds exceeding 900 kilometers per hour sweep across the planet, while occasional storms punctuate the atmosphere, hinting at deeper processes. The methane that dominates the upper layers not only gives Uranus its distinctive color, but also masks more complex chemistry occurring at greater depths. Recent detections of trace compounds, such as hydrogen sulfide, add to the growing understanding of Uranus' atmospheric composition. Probing these layers could reveal the interplay of chemistry, temperature, and pressure that drives the planet's unique weather patterns. The thermal mystery of Uranus remains one of its most enduring puzzles. Unlike its neighbor Neptune, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This lack of internal heat could stem from its unique internal structure, where insulating layers of ice trap heat deep within. Alternatively, the hypothesized collision that tilted Uranus on its side might have expelled much of its primordial heat into space. Solving this mystery could offer new perspectives on how planets retain or lose energy over time, with implications for both the solar system and exoplanetary science. The magnetic field of Uranus is another anomaly that defies easy explanation. Tilted and offset from the planet's center, it creates a lopsided magnetosphere that behaves unpredictably. This chaotic field interacts with the solar wind in unique ways, generating auroras that are unlike those seen on Earth or other planets. Studying these interactions could provide valuable data on the processes that shape magnetic fields and their impact on planetary environments, including the shielding of atmospheres from solar radiation, a critical factor in determining habitability. A dedicated mission to Uranus would address these mysteries and unlock a wealth of knowledge about the planet, its system, and the broader context of ice giants in the universe. Such a mission could include an orbiter to study the planet's magnetic field, atmosphere, and rings over an extended period, as well as probes to descend into the atmosphere and landers to explore the moons. High-resolution imaging and spectrometry could provide unprecedented views of Uranus moons, revealing surface features, detecting potential subsurface oceans, and analyzing their compositions. The implications of studying Uranus extend beyond the planet itself. Ice giants like Uranus are among the most common types of planets in the galaxy. By understanding the properties and behaviors of Uranus, we gain a blueprint for interpreting data from exoplanets, refining models of their atmospheres, interiors, and magnetic fields. These insights are essential for determining the potential habitability of distant worlds and for understanding the diversity of planetary systems. The exploration of Uranus is not just a scientific imperative. It is a testament to humanity's enduring curiosity and determination to explore the unknown. Its mysteries challenge us to think creatively, innovate, and push the boundaries of what is possible. Each discovery made on Uranus will deepen our understanding of the cosmos, inspire future generations of explorers, and strengthen our connection to the universe. As we stand on the threshold of a new era in space exploration, Uranus shines as a beacon of possibility. Its secrets await, ready to transform our understanding of the solar system and the broader galaxy. The journey to uncover them will be challenging, but the rewards, knowledge, inspiration, and a deeper sense of our place in the universe are immeasurable. Let us rise to the challenge, answer the call, and unlock the mysteries of Uranus, a world that holds the keys to understanding the cosmos and our shared journey through the stars. The journey to Uranus is a mission that calls for ingenuity, persistence, and the unrelenting human drive to uncover the unknown. It represents a profound opportunity to explore a world that challenges every expectation, offering clues to the forces that shape not just our solar system, but planetary systems across the universe. Uranus, with its unique features and unexplored mysteries, is more than a distant giant. It is a frontier that invites us to redefine our understanding of planets, their formation, and their evolution. One of the most compelling aspects of Uranus is the evidence of its tumultuous past. The planet's dramatic axial tilt, rotating almost sideways, marks it as an outlier among its peers. If this orientation was caused by a massive collision, the event would have left an indelible mark on Uranus and its system. The debris from such an impact may have formed the rings or influenced the orbits of its moons, while the redistribution of energy within the planet itself could have disrupted its thermal and magnetic properties. Alternatively, a gravitational tug-of-war with neighboring giant planets or a rogue celestial body might have tipped Uranus into its current orientation. Understanding the cause of this tilt will require a detailed examination of the planet's internal structure, atmosphere, and magnetic field. The magnetic field of Uranus remains one of its most perplexing features. Unlike the relatively aligned magnetic fields of Earth or Jupiter, Uranus' field is tilted nearly 60 degrees from its rotational axis and offset significantly from the planet's center. This irregularity creates a chaotic magnetosphere that interacts with the solar wind in unexpected ways. Auroras dance across the planet, but not at the poles where they typically appear. Instead, they light up in scattered, unpredictable regions. Studying these phenomena could provide a window into the mechanics of magnetic fields, which play a critical role in shaping planetary atmospheres and shielding them from solar radiation. Insights from Uranus' magnetic field could inform models of exoplanetary magnetospheres, many of which may resemble those of ice giants. The planet's moons, each with its own distinct characteristics, offer a microcosm of geological and potentially hydrological activity. Miranda, with its dramatic cliffs and chaotic terrain, is a world of extremes. Its surface features suggest cycles of tidal heating and freezing that may have reshaped it multiple times. Ariel, with its smooth plains and signs of cryovolcanism, indicates a geologically active past, while Titania and Oberon may conceal subsurface oceans beneath their ancient, cratered exteriors. These hidden oceans, if they exist, would be shielded from the harsh conditions of space, providing environments where water, energy, and chemistry interact, a combination that raises tantalizing questions about the potential for life. Exploring these moons could revolutionize our understanding of habitability in the outer solar system. Subsurface oceans are considered some of the most promising environments for prebiotic chemistry, and finding even the faintest traces of organic molecules or energy gradients could transform our understanding of the conditions necessary for life. The icy moons of Uranus may join Europa and Enceladus as prime candidates in the search for life beyond Earth. Uranus rings, though faint and understated, are no less significant. Their composition of dark, carbon-rich materials suggests a history of collisions and fragmentation. These rings may be remnants of a moon or other body that was shattered by an impact or torn apart by Uranus' gravity. Their narrow and sharply defined edges hint at the presence of shepherd moons, small satellites whose gravitational influence maintains the ring's structure. Understanding how these rings formed and evolved could provide insights into the processes that govern ring systems across the solar system, from Saturn's majestic rings to Neptune's faint arcs, and even the rings of exoplanets. The atmosphere of Uranus presents another compelling mystery. Its calm, bluish appearance hides powerful winds that race at supersonic speeds, driven by processes that remain poorly understood. The methane in the upper atmosphere, not only gives Uranus its color, but also obscures deeper layers where more complex chemistry may occur. Occasional storms and bright spots suggest dynamic weather patterns, while the recent detection of trace compounds such as hydrogen sulfide adds to the growing picture of Uranus' atmospheric complexity. Probing these layers could uncover the interactions between chemistry, temperature, and pressure that shape the planet's weather and provide clues to its origins. The thermal properties of Uranus set it apart from all other planets. While most giant planets radiate more heat than they receive from the Sun, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This lack of internal heat could result from its unique internal structure, with layers of ice insulating the core and trapping any remaining warmth. Alternatively, the hypothesized collision that tilted Uranus may have ejected much of its heat into space. Understanding this thermal deficit could have far-reaching implications for how planets store and lose energy over time, particularly for ice giants in our solar system and beyond. A mission to Uranus represents a monumental step forward in planetary science. Equipped with modern technology, an orbiter could provide long-term monitoring of the planet, capturing seasonal changes, mapping its magnetic field, and analyzing its atmosphere. Probes could descend into the clouds to directly measure temperature, pressure, and composition, while landers or flybys of its moons could search for signs of geological activity and subsurface oceans. Such a mission would not only solve long-standing mysteries about Uranus, but also provide a wealth of data to inform our understanding of ice giants and their role in the solar system. The implications of exploring Uranus extend beyond the planet itself. Ice giants like Uranus are among the most common types of planets discovered in other star systems. By studying Uranus, we can refine our models of their atmospheres, interiors, and magnetic fields, gaining insights into the nature of these distant worlds. The discoveries made on Uranus will also shape our search for habitable environments and the potential for life in icy regions of the universe. The journey to Uranus is a journey of discovery, innovation, and inspiration. It is a mission that embodies humanity's desire to explore, to understand, and to connect with the universe. The answers hidden within Uranus' icy depths promise to transform our knowledge of the cosmos, offering new perspectives on the forces that shape planetary systems and the potential for life beyond Earth. As we look to the future, the call to explore Uranus grows ever stronger. Its mysteries await, ready to inspire a new generation of scientists, engineers, and explorers. The journey to Uranus is not just about solving puzzles. It is about expanding the boundaries of human knowledge and embracing the wonder of discovery. It is a journey that connects us to the stars and reminds us of our shared quest to understand the cosmos. Let us rise to the challenge, answer the call, and unlock the secrets of Uranus, a world that holds the keys to understanding our place in the universe. The journey to Uranus represents not just a leap into the distant reaches of our solar system, but also an exploration of some of the most profound questions about planetary formation, evolution, and the potential for life in unexpected places. Uranus is a world of contradictions and extremes, a planet whose serene appearance masks dramatic histories, volatile dynamics, and a complexity that defies easy explanation. To understand Uranus is to peel back the layers of a cosmic puzzle that could fundamentally reshape our understanding of not only ice giants but also the very processes that govern planetary systems across the galaxy. At the heart of Uranus' mystery is its internal structure, where exotic materials and conditions challenge our current models of planetary interiors. Beneath its atmosphere lies a vast, icy mantle composed of water, ammonia, and methane under immense pressure and heat. This mantle may contain regions of superionic water, a phase of matter where hydrogen ions flow freely through a solid lattice of oxygen. Such an environment would create conditions ripe for generating the chaotic magnetic field that Uranus exhibits. This field, tilted and offset from the planet's center, creates a lopsided magnetosphere that interacts unpredictably with the solar wind. Understanding how this magnetic field is generated and maintained is crucial not only for Uranus, but also for modeling the magnetic environments of distant exoplanets. The planet's moons, scattered across a range of sizes and geologies, are a microcosm of the dynamic forces that shape icy bodies in the outer solar system. Each moon tells its own story. Miranda's jagged cliffs and patchwork surface hint at cycles of tidal heating and resurfacing that could still be active today. Ariel's fractured plains and smooth regions suggest cryovolcanism, a process where icy materials, rather than molten rock, flow and freeze on the surface. Titania and Oberon, Uranus' largest moons, may conceal subsurface oceans beneath their ancient, cratered exteriors. These hidden seas, warmed by radioactive decay or tidal forces, could harbor environments where water, heat, and organic molecules interact. Such interactions are among the key ingredients for prebiotic chemistry, and discovering them on Uranus moons would be a groundbreaking step in the search for extraterrestrial life. The potential habitability of Uranus moons elevates them to high-priority targets for exploration. Subsurface oceans are not merely theoretical possibilities. They are becoming increasingly plausible based on our understanding of similar icy bodies, such as Europa and Enceladus. Probing these moons for heat signatures, detecting chemical markers of organic processes, or even observing indirect evidence of water plumes could provide the first concrete evidence of life-friendly environments beyond Earth. These discoveries would revolutionize our understanding of the conditions under which life might emerge and thrive in the universe. The rings of Uranus, though subtle and understated, hold secrets about the planet's past and the forces that sustain their structure. Their dark, carbon-rich composition suggests a history of fragmentation and collision, possibly the remnants of a moon destroyed by an impact or tidal forces. The sharp boundaries of these rings, maintained by the gravitational influence of shepherd moons, reflect a delicate interplay of forces that has persisted for millions or even billions of years. Studying these rings offers a unique opportunity to understand the life cycle of ring systems, from their formation to their eventual dissipation. These insights are critical not only for Uranus but also for Saturn's rings, Neptune's arcs, and the ring systems of exoplanets. Uranus' atmosphere, while deceptively calm at first glance, reveals a hidden world of extremes. Winds reaching supersonic speeds sweep across the planet, driven by mechanisms that remain poorly understood. Bright storms occasionally surface. Alternatively, the hypothesized collision that tilted Uranus on its side may have ejected much of its primordial heat into space. Solving this mystery could provide profound insights into how planets lose and retain energy, offering clues to the thermal evolution of ice giants and exoplanets with similar characteristics. A dedicated mission to Uranus would address these mysteries and open new horizons in planetary science. An orbiter equipped with cutting-edge instruments could monitor the planet's atmosphere, magnetic field, and rings over an extended period, capturing seasonal changes and dynamic events. Probes sent into the atmosphere could directly measure its composition, temperature, and pressure, while landers or flybys of its moons could search for geological activity and evidence of subsurface oceans. Such a mission would not only answer long-standing questions about Uranus, but also provide a wealth of data to inform future exploration of similar planets. The implications of studying Uranus extend far beyond its icy domain. Ice giants like Uranus are among the most common types of planets found in the galaxy, making them essential to understanding the diversity of planetary systems. By exploring Uranus, we gain a blueprint for interpreting the atmospheres, magnetic fields, and internal structures of distant exoplanets. These discoveries will also inform the search for habitable environments, guiding the next generation of telescopes and missions in the hunt for life beyond Earth. Uranus challenges us to think bigger, to venture farther, and to embrace the unknown. Its mysteries are not merely puzzles to be solved. They are opportunities to expand our understanding of the cosmos and our place within it. The journey to Uranus is a journey of discovery, innovation, and inspiration. It is a mission that reflects humanity's unyielding curiosity and our determination to push the boundaries of what is possible. As we stand on the brink of this new era in exploration, Uranus beckons with the promise of transformative discoveries. Its secrets await, ready to reshape our understanding of the solar system and inspire generations to come. The journey to Uranus is not just about unlocking the mysteries of one planet. It is about connecting with the universe itself and embracing the endless possibilities it holds. Let us rise to the challenge and embark on this extraordinary adventure, unlocking the secrets of Uranus and deepening our connection to the stars. The journey to Uranus is more than a quest to explore an enigmatic world. It is an opportunity to understand the forces that govern the cosmos. Uranus, with its distinct characteristics and unresolved mysteries, is a living laboratory for testing theories about planetary formation, dynamics, and evolution. By answering the questions it poses, we gain not only insight into this unique planet, but also a clearer understanding of the processes shaping worlds across the galaxy. A critical aspect of Uranus' story lies in its striking axial tilt. This unusual orientation, rotating almost horizontally relative to its orbit, has profound effects on the planet's climate, magnetosphere, and system of moons and rings. Seasonal changes on Uranus are among the most extreme in the solar system, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. This cycle creates conditions that are vastly different from those on Earth or other planets, influencing atmospheric circulation and weather patterns in ways we are only beginning to comprehend. Understanding how such a tilt impacts planetary systems could shed light on similar phenomena observed in exoplanets with extreme axial inclinations. The internal structure of Uranus, hidden beneath its atmospheric layers, offers another tantalizing puzzle. Models suggest a rocky core surrounded by a dense, icy mantle composed of water, ammonia, and methane. This mantle is thought to behave like a fluid under the immense pressures and temperatures present inside the planet. Such conditions could give rise to exotic phases of matter, including superionic water, where hydrogen ions move freely within a solid lattice of oxygen. This unique state of matter might play a key role in generating Uranus' irregular magnetic field, which is tilted and offset from the planet's center. Studying this phenomenon could revolutionize our understanding of how magnetic fields are generated on ice giants and other planetary bodies. The moons of Uranus, each with its own distinct geology, hold clues to the planet's history and the dynamic forces at work within its system. Miranda, with its towering cliffs and chaotic surface, appears to have undergone multiple cycles of disruption and renewal. Tidal heating, caused by gravitational interactions with Uranus, may have periodically melted its interior, reshaping the surface with each episode. Ariel, with its smooth plains and extensive fault lines, suggests a history of cryovolcanism, where icy materials erupted onto the surface and froze in place. Titania and Oberon, Uranus' largest moons, are less dynamic on the surface, but may harbor subsurface oceans beneath their icy exteriors. These hidden oceans, sustained by internal heat, represent potential habitats for microbial life, a possibility that elevates the significance of these moons in the search for extraterrestrial life. The exploration of Uranus moons could reveal much about the conditions necessary for sustaining life in icy environments. Subsurface oceans, insulated from the harsh conditions of space by thick ice layers, provide environments where water, energy, and nutrients might combine to create the building blocks of life. The detection of such oceans, or the chemical markers of organic processes, would not only transform our understanding of habitability, but also expand the scope of astrobiology to include icy moons as potential homes for life. The rings of Uranus, though faint and narrow, are no less intriguing. Their dark, carbonaceous material suggests a history of fragmentation and collision, likely involving a moon or other body that was destroyed long ago. These rings are among the youngest in the solar system, indicating that the processes shaping Uranus' system are still active today. The presence of sharp edges and narrow bands points to the influence of shepherd moons, whose gravitational forces maintain the structure of the rings. Studying these dynamics could provide valuable insights into the formation and evolution of ring systems, both within our solar system and in distant exoplanetary systems. Uranus' atmosphere, with its calm blue-green appearance, conceals powerful dynamics driven by extreme conditions. Winds exceeding 900 kilometers per hour sweep across the planet, creating jet streams and vortices that are still poorly understood. Occasional storms and bright features suggest bursts of convective activity, possibly linked to deeper layers of the atmosphere. The methane in the upper atmosphere, which gives Uranus its distinctive color, absorbs red light, but also masks more complex processes occurring beneath. Probing these layers could reveal the intricate chemistry, pressure, and temperature interactions that drive Uranus' weather and contribute to its atmospheric evolution. The absence of significant internal heat is perhaps Uranus' most puzzling feature. Unlike Neptune, which radiates more energy than it receives from the Sun, Uranus emits almost no excess heat, making it uniquely cold among the planets. This anomaly could be tied to the planet's internal structure, with insulating layers of ice trapping heat deep within. Alternatively, the violent collision that tilted Uranus on its side may have expelled much of its primordial heat into space. Solving this mystery would provide critical insights into how planets store and release energy over time, influencing their evolution and dynamics. A dedicated mission to Uranus would address these compelling questions and push the boundaries of planetary science. An orbiter equipped with state-of-the-art instruments could monitor the planet's magnetic field, atmosphere, and rings over time, capturing seasonal changes and dynamic events. Atmospheric probes could measure composition, temperature, and pressure directly, while landers or flybys of the moons could search for evidence of subsurface oceans, geological activity, and chemical signatures of organic processes. Such a mission would not only transform our understanding of Uranus, but also provide a wealth of data applicable to the study of other ice giants and exoplanets. The significance of Uranus extends far beyond its own system. Ice giants like Uranus are among the most common types of planets found in the galaxy, making them crucial to understanding planetary diversity and evolution. By exploring Uranus, we gain a template for interpreting the properties of distant worlds, refining models of their atmospheres, interiors, and magnetic fields. The discoveries made on Uranus could shape the next generation of exoplanet studies, guiding the search for habitable environments and the potential for life beyond our solar system. The exploration of Uranus is a bold undertaking, one that reflects humanity's enduring curiosity and determination to understand the cosmos. Its mysteries challenge us to think creatively, to innovate, and to push the boundaries of what is possible. Each question answered about Uranus brings us closer to understanding the forces that shape the universe and our place within it. As we stand on the cusp of this extraordinary journey, Uranus beckons with the promise of transformative discoveries. Its secrets await, ready to inspire and enlighten, to fuel the dreams of explorers and scientists for generations to come. The journey to Uranus is not just about unlocking the mysteries of a distant planet. It is about embracing the wonder of discovery, connecting with the universe, and expanding the horizons of human knowledge. Let us rise to this challenge, venture into the unknown, and uncover the secrets of Uranus, a world that holds the key to understanding the cosmos and our place within it. The exploration of Uranus represents one of the greatest opportunities for advancing our understanding of the solar system. Its icy, distant world holds the promise of unlocking answers to questions that reach far beyond its serene, blue-green appearance. Every aspect of Uranus, from its peculiar tilt and unique magnetic field to its mysterious moons and faint rings, points toward fundamental processes that govern not only our own planetary neighborhood, but also the thousands of exoplanetary systems we are now discovering across the galaxy. The axial tilt of Uranus stands as a profound mystery and a signature of its tumultuous past. Unlike any other planet, Uranus spins almost entirely on its side, creating extreme, seasonal variations that last decades. This tilt has a cascading effect on its moons, rings, atmosphere, and magnetic field. It suggests a violent and chaotic history, potentially caused by a massive collision with a protoplanet or a series of gravitational interactions with other bodies in the early solar system. The debris from such events might explain the formation of its rings and the rearrangement of its moons, but confirmation requires a deep dive into the planet's composition and orbital dynamics. The planet's magnetic field is no less curious. Misaligned and offset, it creates a magnetosphere that wobbles unpredictably as Uranus rotates. This erratic behavior generates auroras in unexpected locations, revealing how Uranus interacts with the solar wind. Studying its magnetic field provides a natural experiment in planetary magnetism, offering a window into how such fields are generated by internal dynamos in environments vastly different from Earth. Insights gained here could help us understand magnetic fields on distant exoplanets, where similar dynamics might shape their atmospheres and potential habitability. The moons of Uranus, scattered across a spectrum of sizes and geological activity, are another key to understanding its history. Miranda, with its towering cliffs and chaotic surface features, suggests repeated cycles of tidal heating and internal reshaping. This heating may have melted parts of its interior in the past, allowing icy material to well up and refreeze, creating the distinctive patchwork terrain observed today. Ariel, one of the most intriguing moons, shows evidence of extensive fault lines and cryovolcanism, hinting at a geologically active history that might still persist in some form. Titania and Oberon, the largest moons, are older and more heavily cratered, yet their surfaces show subtle hints of fractures and ridges, suggesting internal processes that shaped them long ago. The potential for subsurface oceans beneath their icy shells makes these moons particularly exciting targets for future exploration. If these oceans exist, they could be sites of active chemistry, where water, heat, and organic molecules interact, conditions that are essential for life as we understand it. The discovery of subsurface oceans on Uranus moons would have profound implications for astrobiology. These hidden seas would represent isolated environments shielded from space's harsh conditions, creating stable niches where complex chemical processes might unfold. Investigating these environments could expand our understanding of habitability, demonstrating that life-sustaining conditions might exist in far more places than previously thought. Even if these oceans are sterile, their discovery would reshape our understanding of the diversity of planetary systems and the potential for life beyond Earth. The rings of Uranus, though faint and narrow, are rich with scientific intrigue. Their dark composition and sharply defined structure suggest an origin tied to past collisions and the gravitational shepherding of small moons. These rings may be younger than the planet itself, reflecting ongoing processes that shape and sustain them. By studying their composition, structure, and dynamics, scientists can learn how such systems form, evolve, and interact with their host planets. These insights are not just relevant to Uranus. They inform our understanding of other ring systems, including those around Saturn and exoplanets with similar features. The atmosphere of Uranus, deceptively calm at first glance, hides powerful dynamics beneath its placid appearance. Winds race at incredible speeds, and occasional storms suggest bursts of convective activity. The methane that dominates the upper atmosphere gives the planet its distinctive color, but also conceals deeper layers where temperatures and pressures create exotic conditions. These hidden depths may contain complex chemical interactions that hold clues to the planet's formation and evolution. Probing these layers with atmospheric instruments could reveal the pathways by which Uranus assembled its icy mantle and what role it played in the early solar system. The absence of significant internal heat on Uranus remains a cornerstone mystery. Unlike other giant planets, which radiate more energy than they receive from the sun, Uranus emits almost no excess heat, making it uniquely cold. This anomaly could be tied to the planet's internal structure or a violent event in its past that expelled much of its primordial heat. Understanding this thermal deficit could reshape theories about planetary energy budgets, offering insights into how planets lose or retain heat over billions of years. A dedicated mission to Uranus is not only an exploration of the planet, but also an investment in the future of planetary science. Equipped with modern technology, such a mission could deploy orbiters, probes, and flybys to study the planet's atmosphere, rings, and moons in unprecedented detail. High-resolution imaging and spectroscopic analysis would reveal the composition and activity of Uranus' system, while magnetic field measurements and atmospheric probes would uncover the internal processes driving its unique characteristics. Exploring its moons could uncover signs of subsurface oceans, active geology, or even the precursors of life. The data gathered from a mission to Uranus would ripple across the scientific community, informing studies of ice giants, exoplanets, and planetary systems as a whole. Ice giants like Uranus are among the most common types of planets in the galaxy, and studying this one up close provides a template for understanding countless others. These insights could shape the next generation of exoplanet exploration, refining models of planetary atmospheres, interiors, and habitability. Uranus challenges us to think bigger, to explore further, and to embrace the unknown. Its mysteries are not just questions to be answered. They are opportunities to expand our horizons and deepen our connection to the cosmos. The journey to Uranus is a journey of discovery, innovation, and inspiration, a mission that reflects humanity's enduring curiosity and our determination to push the boundaries of knowledge. As we stand at the brink of this extraordinary endeavor, the call to Uranus grows louder. Its secrets await, ready to transform our understanding of the universe and inspire future generations of scientists and explorers. The journey to Uranus is not merely about solving puzzles. It is about celebrating the wonder of discovery and connecting with the cosmos in a profound and meaningful way. Let us rise to this challenge, embrace the unknown, and uncover the secrets of Uranus, a world that holds the key to understanding our place in the universe and the limitless possibilities beyond. The call to explore Uranus echoes as a defining moment in our quest to understand the cosmos. This icy giant, with its serene outward appearance masking a chaotic and dynamic interior, represents the perfect blend of mystery and potential. Each unanswered question about Uranus points toward discoveries that could reshape our understanding of planets, from their formation to their evolution, and even their potential to harbor life. The axial tilt of Uranus is a testament to the chaos of the early solar system, an artifact of a violent and transformative event billions of years ago. This extreme orientation, rolling almost sideways in its orbit, has given rise to unique conditions that influence the planet's seasons, atmosphere, and magnetosphere. These conditions challenge the way we think about planetary dynamics, urging us to explore how such an unusual tilt could impact the development and long-term stability of a planetary system. By understanding Uranus' tilt, we not only unravel its own history, but also gain insights into the complex gravitational interplay that defines planetary systems across the galaxy. Its moons provide a microcosm of the diversity and activity that icy worlds can offer. Each moon adds a unique chapter to Uranus' story. Miranda's chaotic terrain, scarred by cliffs and canyons, reflects a history of tidal forces that reshaped its surface repeatedly. Ariel's smooth plains and intricate fault systems speak of a geologically active past, potentially driven by cryovolcanism. Titania and Oberon, though appearing more ancient and cratered, may hold surprises beneath their surfaces. Oceans warmed by residual heat and insulated by thick ice layers. Such environments could be among the most promising locations for the study of life's potential beyond Earth. These moons not only captivate our imagination, but also challenge our understanding of habitability. Subsurface oceans, if present, offer an extraordinary opportunity to study environments isolated from the harshness of space, yet dynamic enough to support chemical processes essential for life. The discovery of such oceans would redefine the concept of habitable zones, showing that life-friendly conditions can exist far from the warmth of a star. By probing these moons, we take a step closer to answering the profound question of whether we are alone in the universe. The rings of Uranus, faint yet structurally complex, reveal an ongoing dance of gravitational forces. Their dark, carbon-rich material suggests a past marked by collisions and fragmentation, perhaps involving a shattered moon or captured object. These rings, sharply confined and precisely ordered, point to the influence of shepherd moons, tiny satellites whose gravitational pull maintains the ring's boundaries. Investigating their composition, origin, and dynamics would provide insights into the forces shaping not only Uranus rings, but also those of other planets, from Saturn to the barely visible arcs of Neptune. The planet's magnetic field stands as one of its most striking anomalies. Tilted dramatically and offset from the planet's center, it creates a magnetosphere that is chaotic and ever-changing. Auroras flicker unpredictably across Uranus' atmosphere, driven by the interaction of the solar wind with this irregular field. Understanding how such a magnetic field is generated within Uranus' icy mantle could unlock secrets about magnetic dynamos in other worlds, including exoplanets that exhibit similar features. These findings could inform how magnetic fields influence atmospheric retention, surface conditions, and even the habitability of distant worlds. The atmosphere of Uranus, often described as deceptively calm, hides a realm of powerful forces and intricate chemistry. Supersonic winds sweep across its surface, driven by internal dynamics that remain poorly understood. Methane in the upper atmosphere absorbs red light, giving the planet its striking color, while concealing deeper layers where pressures and temperatures rise dramatically. Occasional storms suggest that Uranus is far from static, with bursts of activity hinting at underlying processes that remain mysterious. Probing the atmosphere could reveal how the planet's chemistry has evolved and provide a window into the materials and conditions that shaped the early solar system. The thermal mystery of Uranus remains a cornerstone question. Unlike other giant planets, which radiate significant heat left over from their formation, Uranus emits almost no excess energy, making it the coldest planet in the solar system. This anomaly could be tied to its unique internal structure, where thick layers of ice trap heat deep within, or to the violent event that tilted the planet and potentially released much of its primordial heat. Solving this puzzle would deepen our understanding of how planets lose or retain energy over billions of years, offering broader insights into planetary thermodynamics. A mission to Uranus would mark a monumental leap forward in planetary exploration. The tools at our disposal today, advanced orbiters, atmospheric probes, and landers, could unlock the secrets of this distant world in ways that were unimaginable during Voyager 2's fleeting flyby. An orbiter could monitor seasonal changes, map the magnetic field, and capture high-resolution images of the planet, its moons, and its rings. Probes could dive into the atmosphere, measuring its composition, pressure, and temperature directly. Flybys of the moons could search for geological activity, subsurface oceans, and the chemical signatures of organic processes. The discoveries made at Uranus would resonate far beyond our solar system. Ice giants like Uranus are among the most common types of planets found in exoplanetary systems. By studying Uranus, we establish a foundation for understanding the properties of these distant worlds, refining our models of their atmospheres, interiors, and potential for habitability. The lessons learned at Uranus will guide future missions to exoplanets, bringing us closer to answering fundamental questions about the diversity of planetary systems and the conditions necessary for life. The exploration of Uranus is not merely an opportunity to study a planet. It is a testament to humanity's insatiable curiosity and our desire to push the boundaries of what is possible. Its mysteries challenge us to innovate, to think creatively, and to reach for answers that lie beyond our current grasp. Each discovery made at Uranus will deepen our understanding of the universe and inspire the next generation of explorers, scientists, and dreamers. As we stand at the dawn of this new era of exploration, Uranus beckons with the promise of transformative discoveries. Its secrets, hidden within its atmosphere, rings, and moons, are waiting to be uncovered, offering a glimpse into the forces that shape the cosmos. The journey to Uranus is not just about solving puzzles. It is about expanding the horizons of human knowledge, embracing the wonder of the unknown, and connecting with the vast and intricate universe we call home. Let us answer this call, embark on this extraordinary adventure, and uncover the secrets of Uranus, a world that holds the keys to understanding the cosmos and humanity's place within it. The exploration of Uranus represents one of humanity's most profound opportunities to connect with the mysteries of the cosmos. It is a planet that challenges our assumptions, offering insights into the forces that shape the solar system and continue to govern the universe. As we strive to understand Uranus, we are embarking on a journey that will not only reveal its secrets but also expand the boundaries of science, technology, and imagination. Central to the intrigue of Uranus is the enduring mystery of its extreme axial tilt. Unlike any other planet in the solar system, Uranus rotates on its side, creating an extraordinary seasonal dynamic. Each hemisphere experiences decades-long periods of continuous sunlight followed by equally long stretches of darkness. These extremes influence everything from atmospheric circulation to the behavior of its moons and rings. The tilt also raises fundamental questions about the stability and evolution of planetary systems. Did Uranus' tilt result from a colossal impact in its early history, or was it the product of a slow gravitational dance with other massive bodies? Answering these questions will require not only detailed observation, but also advanced modeling of the planet's dynamics and interactions. The planet's internal structure remains another tantalizing puzzle. Beneath its icy surface lies an environment of immense pressure and temperature, where exotic materials like superionic water may exist. This phase of water, where hydrogen ions flow freely while oxygen atoms form a lattice, could be a key factor in generating Uranus' chaotic magnetic field. The field itself is a study in extremes, tilted and offset in a way that creates a lopsided magnetosphere. As the planet rotates, this irregular field interacts unpredictably with the solar wind, producing auroras and magnetic disturbances that defy comparison with any other planet. Studying these interactions will not only clarify the processes at work within Uranus, but also inform our understanding of magnetic fields on distant exoplanets. Uranus moons hold equal promise for discovery. Miranda's surface, with its towering cliffs and bizarre patchwork of terrain, tells a story of tidal forces and geological upheaval. This history of resurfacing suggests a dynamic interior, possibly influenced by past or ongoing tidal heating. Aerial smooth plains and cryovolcanic features hint at processes that may still be active beneath its icy crust. Titania and Oberon, the largest moons, are particularly intriguing due to the potential for subsurface oceans. If these hidden seas exist, they could be sites of complex chemical reactions, where water, heat, and organic compounds interact in conditions similar to those that may have given rise to life on Earth. The discovery of subsurface oceans on Uranus moons would redefine the boundaries of habitability. These isolated environments, shielded from the harshness of space, represent some of the most promising locations in the solar system to search for life. The presence of liquid water, combined with potential energy sources from tidal heating or radioactive decay, could create conditions where simple microbial life might thrive. Even if these moons prove sterile, their study will vastly expand our knowledge of the diverse environments where life could potentially emerge. The rings of Uranus, though faint compared to Saturn's, are another window into the planet's dynamic history. Their dark, carbon-rich material points to origins tied to destruction, likely the remnants of a shattered moon or other body. These narrow and sharply defined rings reflect the gravitational influence of shepherd moons, which maintain their structure. Studying the composition, age, and behavior of these rings could offer insights into the processes that shape ring systems across the solar system and beyond. These lessons extend to exoplanets, where similar features might exist but remain hidden due to their immense distances. Uranus' atmosphere, deceptively calm in appearance, hides powerful forces beneath its placid surface. Winds travel at supersonic speeds, and occasional storms suggest deep-seated processes driving atmospheric activity. The methane in the upper atmosphere absorbs red light, giving the planet its blue-green color, but it also conceals more complex chemistry occurring at greater depths. Probing this atmosphere could reveal not only the composition of Uranus layers, but also the processes that have shaped its evolution over billions of years. The thermal anomaly of Uranus, the coldest planet in the solar system despite its proximity to the Sun, remains one of its most perplexing features. Unlike Neptune, which radiates significant internal heat, Uranus emits almost no excess energy. This absence of heat could be tied to its internal structure, where a thick, icy mantle insulates the core. Alternatively, it might result from the hypothesized collision that tilted the planet and released much of its primordial energy. Resolving this mystery could have profound implications for our understanding of planetary thermodynamics and the energy budgets of ice giants. A mission to Uranus represents a transformative opportunity for planetary science. An orbiter, equipped with modern sensors, could observe the planet and its system over time, capturing seasonal changes and studying its dynamic features in unprecedented detail. Atmospheric probes could descend into Uranus clouds, measuring temperature, pressure, and composition directly. Flybys of its moons could map their surfaces, search for geological activity, and detect signs of subsurface oceans. Such a mission would not only answer long-standing questions about Uranus, but but also provide insights into the behavior and evolution of ice giants as a class of planets. The implications of studying Uranus extend far beyond the planet itself. Ice giants are among the most common types of exoplanets discovered in the galaxy. By studying Uranus, we gain a template for understanding these distant worlds, refining our models of their atmospheres, magnetic fields, and internal structures. These discoveries will inform the next generation of telescopes and missions, guiding our search for habitable environments and the conditions necessary for life. Uranus challenges us to think creatively, innovate boldly, and embrace the unknown. Its mysteries are not just puzzles to be solved. They are opportunities to expand our knowledge and deepen our connection to the cosmos. The journey to Uranus is a journey of discovery, one that reflects humanity's unrelenting curiosity and our drive to understand the universe. As we stand on the brink of this new era of exploration, Uranus beckons with the promise of profound revelations. Its secrets await, ready to inspire and enlighten, to fuel the dreams of scientists, explorers, and dreamers for generations to come. The journey to Uranus is more than a mission. It is a legacy, an enduring testament to our place in the cosmos and our unyielding desire to reach beyond what we know. Let us rise to this challenge, embark on this extraordinary adventure, and uncover the mysteries of Uranus, a world that holds the keys to understanding our universe and ourselves. The depths of Uranus, a gateway to cosmic understanding. In the vast reaches of our solar system lies Uranus, a planet that defies conventional wisdom and invites us to uncover its secrets. Its serene blue-green appearance is a facade that conceals dynamic forces, unexplored terrains, and extraordinary phenomena. As we delve deeper into Uranus mysteries, we embark on a journey that connects us to the earliest moments of the solar system and the universal principles that govern planetary systems. Uranus is a planet defined by extremes. Its axial tilt, nearly perpendicular to its orbital plane, creates a world where seasons stretch for decades. For over 40 years, one hemisphere is bathed in constant sunlight while the other is cast into perpetual darkness. This unique orientation is a reminder of the violent past that shaped Uranus, a cataclysmic collision or gravitational upheaval that altered its trajectory and redefined its dynamics. The consequences of this event ripple through every aspect of the planet, influencing its atmosphere, rings, and moons. The magnetic field of Uranus is as perplexing as its tilt. Misaligned and offset from the planet's core, it creates a magnetosphere unlike any other in the solar system. This field interacts chaotically with the solar wind, generating auroras that appear in unexpected locations and patterns. Unlike Earth's orderly polar auroras, Uranus' magnetic storms flicker unpredictably, hinting at an internal dynamo shaped by exotic conditions. Beneath the icy mantle, where water and ammonia may exist under extreme pressures, lies the answer to this magnetic irregularity. Understanding Uranus' magnetic field could redefine our knowledge of planetary dynamos, not just for ice giants, but for planets across the universe. Uranus moons, a collection of icy worlds orbiting this tilted giant, add another layer of intrigue. Miranda, with its towering cliffs and patchwork surface, appears to have been reshaped multiple times by tidal forces. Its dramatic terrain suggests that internal heating and external gravitational interactions have driven cycles of melting and refreezing, creating features unique in the solar system. Aerial smoother plains and cryovolcanic flows hint at an active past that may still linger beneath its icy crust. Titania and Oberon, the largest moons, are more ancient and cratered, yet subtle features like fractures and ridges suggest that their interiors could harbor hidden oceans. These subsurface oceans, if confirmed, would transform our understanding of where life might exist in the universe. Isolated from space by thick layers of ice, such oceans could sustain environments where water interacts with energy sources like tidal heating or radioactive decay. These interactions might fuel the chemistry necessary for life, making Uranus moons some of the most exciting candidates for astrobiological exploration. Even if life is absent, the discovery of subsurface oceans would expand our concept of habitability, showing that liquid water, can exist far from the warmth of a star. The faint rings of Uranus add yet another layer to its enigmatic nature. Composed of dark, carbon-rich material, these narrow rings reflect a history of fragmentation and gravitational shepherding. Unlike the bright, expansive rings of Saturn, Uranus rings are subtle, demanding close study to reveal their origins. Were they formed from the remnants of a shattered moon, or are they the product of a more gradual process of erosion and capture? Investigating these rings offers a glimpse into the forces shaping not only Uranus, but ring systems throughout the cosmos. Uranus atmosphere, common appearance, harbors violent winds and bursts of activity. Supersonic jet streams sweep across the planet, creating banded structures visible only in infrared. Occasional storms punctuate the methane-rich atmosphere, their bright spots fleeting evidence of the dynamic processes occurring within. The methane itself absorbs red light, giving Uranus its signature blue-green color, but it also obscures the deeper layers of the planet, where higher pressures and temperatures drive complex chemical interactions. Studying this atmosphere could reveal how Uranus evolved, offering insights into the building blocks of planetary systems. One of the greatest puzzles of Uranus is its coldness. Despite its similarity to Neptune, Uranus emits almost no internal heat, making it the coldest planet in the solar system. This anomaly may be tied to the insulating properties of its icy mantle, or it could result from the ancient collision that expelled much of its primordial energy. Understanding why Uranus lacks internal heat could reveal new principles about planetary thermodynamics and the energy budgets of ice giants, both in our solar system and beyond. A mission to Uranus is more than an exploration. It is an opportunity to unlock the secrets of a planet that defies expectations. Modern spacecraft equipped with advanced sensors could map the planet's magnetic field, study its atmosphere, and capture detailed images of its moons and rings. Probes could descend into Uranus' atmosphere to measure its composition and temperature directly, while flybys of its moons could search for evidence of subsurface oceans, geological activity, and the chemical precursors of life. Each discovery would deepen our understanding of Uranus while providing a template for studying ice giants across the galaxy. The implications of exploring Uranus extend far beyond its icy realm. Ice giants like Uranus are among the most common types of exoplanets discovered. By studying Uranus, we gain a framework for understanding these distant worlds, refining models of their atmospheres, magnetic fields, and internal structures. These insights will guide the next generation of exoplanet exploration, bringing us closer to answering questions about the diversity of planetary systems and the potential for life elsewhere in the universe. Uranus is a world that challenges us to think beyond our current knowledge, to innovate, and to embrace the unknown. Its mysteries are not just puzzles to be solved. They are opportunities to expand our horizons and deepen our connection to the cosmos. The journey to Uranus is a journey of discovery, one that reflects humanity's enduring curiosity and our unyielding drive to understand the universe. As we prepare to embark on this extraordinary adventure, Uranus stands as a beacon of possibility. Its secrets await, ready to inspire generations of scientists, explorers, and dreamers. The exploration of Uranus is not just about unlocking the mysteries of a distant world. It is about connecting with the universe and uncovering the truths that define our place within it. Let us rise to this challenge, embrace the wonder of discovery, and unlock the secrets of Uranus, a gateway to understanding the cosmos and ourselves. The exploration of Uranus is a bold step into the unknown, a venture that promises to redefine what we know about planets, their systems, and the vast mechanisms of the universe. As we continue to unravel its mysteries, Uranus emerges as a cornerstone in our understanding of the cosmic processes that shape not only our solar system, but the countless star systems scattered across the galaxy. At the heart of Uranus' allure lies its origin story, one that remains shrouded in questions. Its extreme axial tilt, where the planet rolls on its side as it orbits the Sun, defies expectations. This tilt has influenced everything from its atmospheric patterns to the behavior of its moons and rings. How did this world come to be so distinct? The prevailing theory suggests a massive collision early in its history. one so catastrophic that it not only knocked the planet sideways, but also disrupted its internal structure, scattering material that might have coalesced into its moons and rings. Yet, alternate theories propose gravitational encounters with other celestial bodies, perhaps even a rogue planet, as the cause of this dramatic reorientation. The implications of understanding Uranus' tilt stretch far beyond the planet itself. Similar disruptions could occur in exoplanetary systems, where planets might experience chaotic interactions or collisions in the crowded early stages of their formation. Uranus serves as a natural laboratory to study the outcomes of such events, providing a window into the chaotic dynamics that may shape planetary systems throughout the universe. Beneath the serene exterior of Uranus' atmosphere lies a complex world of chemistry and physics. The atmosphere, dominated by hydrogen, helium, and methane, appears uniform, yet it harbors supersonic winds and occasional storms that hint at deeper processes. The methane absorbs red light, giving the planet its characteristic blue-green hue, while obscuring the turbulent layers beneath. Recent observations suggest the presence of hydrogen sulfide and other trace gases, which may provide clues about the planet's formation and the primordial materials that compose the early solar nebula. Studying these atmospheric phenomena could reveal how ice giants like Uranus regulate energy, transport heat, and sustain weather systems. The storms, though less frequent than those on Neptune, suggest episodic activity linked to the planet's internal dynamics. This atmospheric complexity also informs our understanding of exoplanets, where similar compositions may drive unique weather patterns and climatic systems. Uranus' magnetic field stands as one of its most striking anomalies. Unlike the aligned and centered magnetic fields of Earth or Jupiter, Uranus' magnetic field is tilted by nearly 60 degrees and offset significantly from its core. This irregular field creates a magnetosphere that twists and warps as the planet rotates, interacting with the solar wind in unpredictable ways. Auroras appear in scattered regions, further complicating the picture of Uranus' magnetic behavior. These unique characteristics challenge existing models of magnetic field generation, which typically rely on convective processes in a planet's core or mantle. Investigating Uranus' magnetic field could provide insights into the role of exotic materials in generating magnetic fields, especially within the icy mantles of ice giants. These findings would have implications for the study of magnetic fields on distant exoplanets, particularly those with unconventional orientations or compositions. The moons of Uranus present a gallery of geological diversity and potential. Miranda, with its dramatic cliffs and chaotic surface, reflects a history of tidal forces and resurfacing. These forces may have melted parts of its icy crust, driving materials to the surface in repeated cycles of renewal. Ariel, another enigmatic moon, shows evidence of cryovolcanism, where icy lava flows smoothed its surface and created vast plains. Titania and Oberon, the largest moons, appear quieter on the surface, but their subtle fractures and ridges hint at internal activity. The potential for subsurface oceans beneath these moons' icy exteriors raises the stakes for exploration. Such oceans, insulated from space and warmed by internal heat, could harbor conditions suitable for life. The discovery of even a sterile ocean would expand our understanding of where liquid water can exist, while finding any signs of organic chemistry would revolutionize our search for extraterrestrial life. These moons, like Europa and Enceladus around Jupiter and Saturn, could become focal points in the quest to understand the building blocks of life in the universe. The rings of Uranus, though less prominent than Saturn's, are equally significant in their complexity. Narrow, dark, and composed of carbonaceous material, these rings are thought to be remnants of a shattered moon or other celestial body. Their sharp boundaries, maintained by gravitational shepherding from small moons, suggest an ongoing balance of forces. Investigating the composition and dynamics of these rings could reveal the history of Uranus' system and the processes that shape ring systems across the solar system and beyond. The absence of significant internal heat from Uranus remains a profound mystery. Unlike Neptune, which radiates more energy than it receives from the Sun, Uranus emits almost no excess heat, making it the coldest planet in the solar system. This thermal deficit could be the result of insulating layers within the planet's interior or a consequence of the hypothesized collision that tipped Uranus and released much of its primordial energy. Solving this puzzle would provide new insights into planetary thermodynamics, offering clues about how energy is stored, transferred, and dissipated in icy worlds. A mission to Uranus would bring clarity to these mysteries and transform our understanding of ice giants. An orbiter could study the planet's magnetic field, atmosphere, and rings over several years, capturing seasonal changes and dynamic events. Probes could descend into the atmosphere, measuring temperature, pressure, and composition, while landers or flybys could investigate the moon's surfaces for geological activity and signs of subsurface oceans. Such a mission would not only answer questions about Uranus, but also lay the groundwork for future exploration of similar worlds in our solar system and beyond. The discoveries made at Uranus would ripple through the scientific community, informing studies of exoplanets, planetary formation, and the search for life. Ice giants like Uranus are among the most common types of planets in the galaxy, making them essential to understanding the diversity of planetary systems. By studying Uranus, we gain a template for interpreting data from these distant worlds, refining our models of their atmospheres, interiors, and magnetic fields. The exploration of Uranus is not just a scientific endeavor. It is a celebration of human curiosity and the drive to understand our place in the cosmos. Each discovery brings us closer to answering the most profound questions about the universe and our role within it. Uranus challenges us to think creatively, to innovate, and to push the boundaries of what is possible. As we prepare to embark on this journey, Uranus stands as a symbol of the vast unknown, a world that invites us to uncover its secrets and deepen our connection to the cosmos. Its mysteries await, ready to inspire future generations and reshape our understanding of the universe. The journey to Uranus is not just about solving puzzles. It is about embracing the wonder of exploration, the power of knowledge, and the limitless possibilities of discovery. Let us rise to this challenge and uncover the truths that lie hidden within Uranus, a gateway to understanding the cosmos and our place within it. The exploration of Uranus is not merely an academic exercise. It is an adventure that beckons humanity to reach beyond the familiar and into the extraordinary. It is a pursuit of answers to questions that have lingered for generations, questions that touch on the origins of our solar system, the dynamics of planetary systems, and the universal conditions that give rise to life. Uranus, with its serene facade and mysterious depths, offers an unparalleled opportunity to deepen our understanding of the cosmos and to inspire future generations of explorers and dreamers. The planet's enigmatic axial tilt serves as a testament to the unpredictability and chaos of planetary evolution. Uranus stands as evidence of how violent and transformative events can shape a world. Theories of a massive collision, a rogue body disrupting its rotation, or gravitational interactions with neighboring planets suggest that Uranus was forged in a crucible of cosmic upheaval. The tilt doesn't just define the planet's unique orientation. It influences its climate, atmospheric circulation, and the stability of its moons and rings. Understanding the mechanics behind this tilt will unlock new perspectives on the forces that govern not only Uranus, but also planets in distant star systems, many of which exhibit similar anomalies. The internal structure of Uranus remains an unsolved puzzle, one that could hold the key to explaining the planet's cold, enigmatic nature. Beneath its atmospheric layers lies an icy mantle where extreme pressures and temperatures create conditions for exotic states of matter. Superionic water, a phase in which hydrogen ions move freely within a lattice of oxygen, is one such possibility. This exotic material could drive the irregularities of Uranus' magnetic field, a chaotic and lopsided system that defies traditional models. By studying Uranus, scientists can test and refine theories about planetary interiors and the generation of magnetic fields, discoveries that will resonate far beyond the icy giant itself. The moons of Uranus provide yet another lens through which to study the planet's history and ongoing activity. Miranda's towering cliffs and chaotic landscapes suggest a moon that has been reshaped multiple times by tidal forces and geological activity. Ariel's fractured surface and cryovolcanic features hint at internal heating that may have driven outflows of icy material onto its surface. Meanwhile, Titania and Oberon, Uranus' largest moons, hold the tantalizing possibility of subsurface oceans, where water, energy, and chemistry could interact to create environments conducive to life. If these moons do indeed harbor oceans beneath their icy shells, they represent some of the most compelling locations in the solar system for studying habitability. These oceans, warmed by residual heat or tidal forces, would be isolated from the harsh vacuum of space, creating stable, potentially life-sustaining environments. Probing these moons for signs of water, organic molecules, or active chemistry could lead to breakthroughs in our understanding of the conditions necessary for life and expand the scope of astrobiology. Uranus rings, subtle and dark, hold their own array of secrets. Their composition and structure reflect a history of collisions and interactions, perhaps involving shattered moons or the gradual erosion of icy bodies. Unlike Saturn's brilliant rings, Uranus rings are faint and narrow, confined by the gravitational influence of shepherd moons. These dynamic systems provide a snapshot of the processes that shape planetary rings, offering a glimpse into similar systems around other planets and even distant exoplanets. Studying these rings will illuminate the delicate balance of forces that maintain their structure and reveal the history of material exchange in Uranus' system. The atmosphere of Uranus, seemingly calm but profoundly dynamic, is a treasure trove of unanswered questions. Supersonic winds, occasional storms, and the striking methane-rich upper layers tell a story of contrasts. Methane gives Uranus its distinctive blue-green color, but it also masks deeper layers where temperatures and pressures rise dramatically. The detection of trace gases, such as hydrogen sulfide, adds to the complexity of the planet's atmospheric chemistry. Exploring these layers with probes and advanced remote sensing technologies could unveil the processes that have shaped Uranus' atmosphere over billions of years, providing insights into its origins and evolution. The thermal anomaly of Uranus, its lack of excess heat, is a defining mystery that challenges our understanding of planetary thermodynamics. Unlike Neptune, which radiates significant heat left over from its formation, Uranus emits almost no additional energy. This raises questions about the planet's internal structure and energy distribution. Did the collision that tilted Uranus also eject much of its primordial heat, or does the planet's icy mantle trap heat within, creating an insulating barrier? Solving this mystery would reveal not only Uranus' unique characteristics, but also broader principles about energy retention and dissipation in planets across the galaxy. A mission to Uranus offers the opportunity to answer these questions and revolutionize our understanding of ice giants. An orbiter could monitor the planet's atmospheric dynamics, map its magnetic field, and study the intricate structure of its rings and moons. Probes sent into the atmosphere could measure its composition, temperature, and pressure, while landers or flybys of the moons could search for evidence of subsurface oceans and active geology. Such a mission would not only unveil the mysteries of Uranus, but also set a new standard for planetary exploration, inspiring future missions to other distant worlds. The significance of studying Uranus extends far beyond its icy realm. Ice giants like Uranus are among the most common types of planets discovered in exoplanetary systems. By exploring Uranus, we create a blueprint for understanding these distant worlds, refining our models of their atmospheres, magnetic fields, and internal structures. These insights will shape the next generation of astronomical research, guiding the search for habitable planets and the conditions necessary for life. The exploration of Uranus is more than a scientific mission. It is a testament to humanity's unyielding curiosity and our desire to push the boundaries of what is known. Each discovery made at Uranus will deepen our understanding of the universe and inspire future generations of scientists, engineers, and explorers. Its mysteries challenge us to think creatively, innovate boldly, and embrace the unknown. As we prepare to embark on this journey, Uranus serves as a symbol of the boundless potential of discovery. Its secrets, hidden within its atmosphere, rings, and moons, are waiting to be revealed, offering profound insights into the forces that shape our cosmos. The journey to Uranus is not just about solving puzzles. It is about celebrating the wonder of exploration, the thrill of discovery, and the limitless possibilities of the universe. Let us answer the call of Uranus, uncover its truths, and forge a deeper connection to the cosmos and our place within it. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.